Now.
Okay, so, okay, I heard you, so good morning. Yeah, welcome to the final day of Code for Earth. It's a pleasure to have you all here. Esperanza and myself, Atina, your contact.
Good morning, everyone.
Okay, so we are here, and I think it has been an interesting ride the last 4 months, going through the coding phase. And before we start with the presentations, we have some housekeeping aspects. And yeah, first of all, we will have a group picture, and we'll do this during the first coffee break. So that will be just outside the entrance. You might have seen the ducks. This is where we're going to meet at 11. And coffee breaks are also in the program. And tonight at 7 o'clock, we will be at a restaurant in the center. I guess you checked out where we go, so we meet there at 7. Health and safety, so we are, we need to make sure that everyone is safe and healthy. So we have fire exits, and there is an assembly area in the car park. And do not leave the site or return to the building if in a case of alarm, unless instructed. An important aspect also, if you leave today, please sign out at the reception. You all signed in, you received your bags. And the assembly area is outside, so when you entered the premises of ECMWF, this is where the assembly area is. In a case of an incident, we don't hope to have that. I guess information about the Wi-Fi is on your badges. You can use the guest Wi-Fi. And you saw where we have tea and coffee served. So it's inside the weather room, but also in the lobby. And as you might have seen this morning, there's also more colleagues here. We have also some colleagues attending today. Get in touch with the people. Use the opportunity being here at the center to get in touch with ECMWF staff and ask the questions you have. And then there are toilets outside the concourse. So we have, the sessions will be 20 minutes plus 5 minutes Q&A. And again, we will have microphones because we have online audience. And this is the opportunity to ask questions to the other teams, get in touch with them. It's networking, it's understanding what the others are doing. So I would recommend use the day very wisely and get in touch with people, connect, because this is what Code for Earth is also about, is connecting people, stay connected, and learn from what others are doing. And we have also a live stream, and there will be probably some questions, or hopefully some questions online, and we will read them out for you. Good. And now we officially start, and I would also like to welcome those people online, in wherever they are on the globe, listening into the final event of Code for Earth 2024 edition. And I would like to hand, I do, okay. So, yeah, some quick facts, especially for those who are listening online. Code for Earth is a key innovation action activity run by ECMWF, the European Center for Medium Range Weather Forecast, and is supported also by Copernicus and Destination Earth. The program runs since 2018, and we had over 59 projects and products coming out of the program. And I have to say, well, we have a phenomenal number of 107 mentors that supported Code for Earth throughout the years, and that is fantastic because we need the mentors. Without the mentors, we cannot run the program. So, and the program welcomes each summer in this 4-month coding phase young talents, as you are, individuals or developer teams from different backgrounds in earth science, computer sciences, and software development. And as I mentioned about innovation, collaboration, a very important aspect, and software development. And for those online, those teams that have been selected and that successfully finished their projects, they will receive a 5,000 euro stipend. This is all the way we have been coming from. So usually end of February, we issue the call for participation. Then Esperanza and myself, we offer 2 Q&A webinars for the broader community. People can ask questions. Then end of April, we announce so people submit their proposals. Then we have an evaluation phase. And end of April, we announce the selected teams, and then in May, you or the selected teams, they go in the coding phase and work with their mentors. And now we reach the final day. That is kind of the celebration of the program for this year. I want to especially thank supporters for this edition. That is Helmholtz Zentrum Herion. Close to Hamburg. They co-mentored or a team, and we are very thankful to have also external mentors joining the program. And I would like to especially mention also IFAP, that's the International Foundation for Big Data and Artificial Intelligence for Human Development. They are based in Italy, in Bologna, and they have been also supporting the program, and unfortunately, because we asked them to briefly introduce IFAP for the ML session, machine learning session, but they weren't able to make it. So, but a special thank to IFAP here as well. And then I would like to hand over to Esperanza.
Hello, everyone. Yeah. Hello, everyone. As Athena says, Code for Earth is a mentorship program. So it means that mentors are a key part for the successful of this initiative. They came up with the original idea of the challenge, they selected the proposal, and also they guide you during the coding phase to help you to develop the outcome you are going to present today. So we are very grateful to all of you present here or online, mentors especially, because their expertise, their commitment, and their free time on the top of their work has been essential for this Code for Earth edition 2024. So as you see on the screen, we have 40 mentors in 2024. So we are very grateful, as I say, to all of you present or online. How many projects have been selected this year? 13 projects. So we are, all of you attending in person or online, are going to show, to display your outcomes. We are very excited to see you, to hear all of you. And I don't know, I'm not going to list everyone. But we are hoping that you are going to surprise ourselves today. Yes, looking ahead, further information. So Code for Earth 2025 is going to happen, so stay tuned. Visit our website regularly and also our socials, because we publish all updates there. So now is the completion of 2024, but some new edition is happening very soon. So this is the useful links, GitHub, our website, and YouTube. The recordings of this session will be published on YouTube shortly. So this is another opportunity to hear yourselves. So now I'm very pleased, to invite Florian Pappenberg. This is the Director of Forecast and Service Department of FISM-WF. So Florian, the floor is yours when you're ready.
Very short. I'm sure you're going to be happy. And as Athena said, good morning.
Good morning.
Oh, close. We're getting there. You know, this afternoon you'll have it. It's fantastic to see you all here. It's great that you're here. It's great that you're at ECMWF, the European Weather Center. As said, I'm the Director of Forecasts and Services, which is one of the departments here at ECMWF. When you walked into this building, you saw these 32 flags outside. Those are the countries which sort of have founded us and created us. Those are the countries which sort of support us in what we do, and also this Code for Earth program, including all these other nice sponsors we had. It's actually quite important. We are quite a simple organization. All we want to do is produce the best weather forecasts in the world, produce high-quality climate information, produce high-quality atmospheric forecasting, and then we do floods and droughts and many other things too. But we're very simple-minded sense. We're trying to produce the best science and innovation which is possible. And that's what we do, and that's why you're here for, and that's why you are here. You sort of described 2018, where we sort of created this program. It was a bit more, I would say, less structured than you made it sound. We actually sat down in this weather room where you had your coffee. You will notice that ECMW's coffee culture is pretty big. Okay, we like our coffee, we really do. Don't take that away from us. Anyway, we sat down there, about 5 people of us, and said, we need to do something new. We need to sort of create innovation. We need to give space for people to do something which they can't do otherwise. It's a bit difficult to do next to their normal jobs, and work with people from the outside who very often have better ideas, mostly often have better ideas than we have internally. So this Code for Earth was called the European Summer of Weather Code at the time, so it was created. Then it became bigger, so it went from weather to earth, obviously. We have more partners, we have more teams, we have more mentors, we have more participants. And I really sort of would like to reiterate, I would like to thank everybody at ECMWF for helped. I would like to thank everybody here in the room who actually helped. We couldn't do this without you. And I've seen some of the results. They are great. And if you look very carefully in the past programs, some of the innovations you are doing actually end up in an operational forecasting chain. Some of the things you do will improve forecast. They will provide better weather forecasts to the world and globally. What else? I think it's quite simple here. You're here to have fun. This is not a work program. This is not a we're meeting our objectives. This is not a whatever KPI type program. It doesn't matter if things fail. It doesn't matter if things are not perfect. We're here to innovate, to try out, and see what we can achieve. I'm really pleased you're all here. I will listen mostly online today because I've got 2 other things to do. But I absolutely love it that you're here. It's great. Talk to all of us. There's many of us in the building. Everybody's usually quite friendly. As I said, if you offer coffee, maybe they're even friendlier. Try that. But just come along. And if you're interested to learn more about ECMWF, just have a look at the web pages. We do loads of other stuff. As I said, Copernicus Climate Change Service, loads of different other types of services in that domain. Or our member states in our different countries. That's all really I had to say. Thank you very much. Great that you're here. That's all I want to say, actually. Forget the rest. Ignore the rest. Thank you.
Thank you, Florian. And yeah, I like your hat. So by the way, you all have hats, so maybe we can have also a picture with the hats. And there's also a sticker in the back. I had difficulties to open it, to get it, but it's nice. So good. Yeah, we had two. Thank you. Good. Thanks. Yeah. At this point, I would like to thank Andy. Big applause. He helped yesterday a lot. So. So let me put this here. Okay, does that work? Yeah, I think so. Good. We had to, mainly for those who are online, we need to change a little bit the order of the agenda because a colleague is stuck in traffic, but he will come later. So, but we are flexible, so we will after Florian's speech, and thanks for that, we will immediately move now to the first presentation, and that's sorry, I have to, Diego, is Martin online? Yeah, because we have, yeah. So we have the challenge that we have some online participants, and we need to get them in. And this moving the agenda slightly has been a last-minute thing. So we need to check if we have some online participants, and we need to get them in. And this moving the agenda slightly has been a last-minute thing, so we need to check if oh, that's me. Martin. Hey, Martin. We have some online participants, and we need to get them in. And this moving the agenda slightly has been a last-minute thing, so we need to check if oh, that's me. Okay, so we start.
That's what I suspected. Hello, good morning.
So Martin Ramacher is one of the...
The problem is, if I talk, I can't hear you because I'm on Zoom and have to watch it on YouTube, so I get feedback, but... No.
He can start.
Hello.
Yeah.
It's on. Hello, good morning. So I need to say a few words instead of Martin. So I work in Copernicus Atmosphere Monitoring Service, and we are producing air quality forecasts for whole Europe. But the resolution of this forecast is coarse, especially for people who are interested in urban air quality. So Martin and Johannes, our co-mentors from the Heron Institute, actually came up with this proposal that we try to see how much extra value we can extract from this raw coarse resolution air quality forecast by introducing other data sets. There are a lot of data sets that you can use, and the challenge of the team was trying to experiment, to see what is available, what they could use, and how much they could improve what our raw forecast skill is. So I think that's my introduction, and I will leave it to you to explain in details what you've done.
Thank you.
All right, so thank you, Micha, for your introduction, and also thank you to Martin and Johannes, who are joining online, for their mentorship during all these 4 months. So, as Micha explained, our objective was to downscale CAMS. And when we first tried to solve the challenge, we first focused on getting data on observation sites as good as we could. So in order to do that, we have several data sets. So we would have the CAMS reanalysis. We focused on the NO2 pollutant, which is a grid of 10 kilometers resolution. Then we have the actual measurements from the European Environmental Agency, which were used to train and validate, and some extra data sets, such as topography, land use, meteorology, build height, population, or even roads. The final product of this first approach are the time series that we can see on the right. So here we can see our model in red, the 10-kilometer CAMS in black, and the actual measurement in blue. We can see that our model successfully reproduces quite well the actual measurements, while the raw CAMS, or the CAMS at 10 kilometers, normally underestimates the actual measurement. So this was our first model, and in order to train it, we used an 80-20 split of the data sets, but not on the station level, but instead on the hour level. So all stations or all measurement sites from the EA were used for both training and validation, which is why we were able to obtain such good results. We then focused on validating this model, and we used the Fermat principles. We used some target diagrams, which, to be super fast and it's super easy to understand, each dot that we see is a station. And we need all stations to be inside the blue circle. The best model is the one that has all the dots at the origin, at 0, 0. On the left, we see the target diagram of CAMS interpolated, so the CAMS at 10 kilometers. And we see that it's actually quite good, because all the dots are inside the circle. But they are quite far away from the origin. On the right, we can see the results for our model. What we have achieved actually is a bias reduction of the CAMS at 10 kilometers. Then we played around by testing different data sets. So training the model using different data sets to see how these data sets improved or worsened our model. So, for example, model version 1091, which is this one over here, has all the data sets. Instead, version 1061 only has topography. In red, on top, we can see the MQI, which is an indicator and is actually the distance between each dot and the origin of the 10-kilometer CAMS. We can see it's quite high, it's near 1, while our model is around 0.5. We saw that there are no significant differences between model versions, which is in part due to the fact that 0.5 is already under the model uncertainty, so we could not improve that any further. So finally, we tested our model in different regions. So on the right, and I know you can see it very small, we can see the MQI for different model versions, so different datasets used, at different cities in the Iberian Peninsula. We can see that the cross would be the 10-kilometer camps, and the dots are our model. We can see that our model is normally better, or is always better than the 10-kilometer camps, and that in some cities the improvement is higher than in other cities. And we also tested that in Poland. We saw that the improvement is more or less the same. We also tested that in Italy, and the results were similar, so we can say that our model generalizes well throughout Europe. Finally, we compared this MQI to the ones obtained from the CAMS European Air Quality Forecast optimized at observation sites product, which has an MQI of 0.3 and 0.5. So if we compare this MQI with our MQI, we can see that we actually don't worsen the actual product. We don't improve it either, we are on par. So next on, we tackled the next challenge, which will be explained by Oscar now.
Thank you. So until now, we have been talking about our model trying to improve the concentration of NO2 at observational sites. But now we wanted to generalize this machine learning model so as to get grid information, which is indeed the aim of the challenge. So, in this approach, we wanted to downscale this CAMS reanalysis data, which is 10 with grid spacing of 10 kilometers, to urban resolution with a grid spacing of 100 meters. So in this case, so as to validate the model in this new approach, we used a different split of data for training and validation. So instead of using an hour split, we used some stations to train the model and some other stations to validate the model. And let's see. So as an example, here we have the city of Barcelona, and here in the left we can see the raw CAMS product, the 10 kilometers product, and then after the downscaling we get this 100 meters map of the city with the concentration of NO2. So to do that, we needed to do some attempts with different model versions. Here, this first image is the first attempt with a model version which doesn't use any extra feature, doesn't use any extra data set. So that's why we cannot recognize the structures of the city. Then we added the topography, and here we can see more or less the urban area and the mountain area behind Barcelona. Then we added also the information of population of the city, and here we can see better the different neighborhoods. And finally, we added also road information and building height information, so as to get this most complete version of the model. So as an example, here we can see a satellite image of Barcelona where we can identify those structures which are taken into account by the model so as to get this concentration map. For example, we can see that the model can identify the city center, which is the area of the city with higher amount of traffic. We can see also, for example, these mountain areas around the city, and also this Montjuic hill inside the city. We can also see the city port, where the concentration, the NO2 concentration is higher. And also we can see some farmland, like the agricultural park of Baix Llobregat, where we can see that the model can identify it due to the fact that it uses also land use data. And the model can also recognize some city highways that surrounds the city, like Ronda de Dalt and Ronda Litoral, which are those two highways. So then, once we got those maps, we wanted to validate also the model. So we got some target diagrams. Here we have the target diagrams for one of the versions. We can see, as expected, that the values are not that close to the origin of the diagram because we didn't use the same splitting method. Now we're trying to get values in a place, in points where no observational data. And here we can see that in this graph, so we can see that most of the versions don't improve the 10 kilometers CAMS product, but those that have all the data set can even improve these 10 kilometers CAMS interpolated. We can see that here as a difference, here we can see a high difference between the different model versions. We can see that the better one is this one. The icons are a little bit moved, so this 2091 corresponds to this this version which has all the data sets. And finally, we got also this this diagram where we can see that now the cross, which corresponds to the row CAMS product, has more or less the same MQI of the different versions of our model, but here we can see that versions are more splitted, so we can see that in general the version 2091 is that one that improved the most the row CAMS product.
Okay, so we have seen what our model achieves in terms of downscaling, what were our results. Now I'm going to present the methodology we followed to achieve this. So we followed more or less a standard machine learning methodology. First, we developed a machine learning model for regression to predict the NO2 values. And we integrated different sources of data, mainly the air quality stations. Yeah. Higher? Like this? Like this? Or?
Put it higher on your line up. That's it.
Okay, thank you. So, yeah, mainly the air quality stations, and then we also added external data sets, such as the topography, the methodology, population, among others. Then in a second step, we performed the validation, which we already presented. And we used the Fairmost standards to validate our model. So we divided this process into 4 steps. First, the data integration, which includes the interpolation of the data sets to the desired resolution, and then also the preprocessing of the data. Then the training of the machine learning model, then the inference to this grid space, to this desired grid space, and finally the validation. So let's start with the model specifications. We targeted the NO2 pollutant with a time resolution of 1 hour during the time period of 2022. And we selected 3 regions, which are the Iberian Peninsula, Italy, and Poland. Inside these regions, we selected the areas with higher density of stations because of 2 reasons. Because first, we assume that these regions are actually the urban areas that we want to target. And secondly, because our model works better when we have high density of stations. So we want to focus on these areas with high density of stations. To do that, we employed a clustering algorithm to identify those high density of these regions of high density for these 3 regions that we have studied. So then, once we have these identified regions with high density, we proceed with the training, and to perform the training, we selected 1 station for each cluster, and then we evaluate the model at this station, and we use all the other stations, all the remaining stations, to interpolate and extract additional features for the model. So we do this interpolation, we integrate all the external data sets at the evaluation point, so the point for which we have selected the evaluation station. And finally, we train a regular regression machine learning model to predict the value at the evaluation point. We repeat this procedure several times, selecting different stations, and for all the time period we have selected. Once we have the model trained, we proceed with the inference. During training, we have trained the model with at evaluation points, but here we want to obtain a final downscaling product, which involves a grid. So here we do instead is we start with the CAMs, and we interpolate the CAMs values using bivariate spline to the desired resolution, which is 100 meters. We also perform interpolation for the stations. In this case, we employed nearest neighbors for the stations to the same resolution we want. And we also do the same process for all the data sets, all the external data sets. So we have, for all the products, the desired output resolution. We integrate all this data, and we input each point in the grid to the model to obtain the final product, which is the downscaling application. So finally, the validation, we follow the fair mode standards, which we already have presented the results according to these standards. So going directly to the future work, first, we think that it's good to study other interpolation methods because, as I said, for example, we use nearest neighbors, and this can be appreciated in the results in these lines that, in the shape of polygons, they are appreciated in the results. So we can study other interpolation methods which are not, which do not present discrete behavior, such as kriging, for example. Then we can also, we think it's important to work in improving the features that we actually have integrated to the model. For example, we have thought that we are using roads. We are using a binary indicator of where there is a road or not, but we could also improve that in a way that for each grid point, we have the distance to each point to a road. Or the last possible future work is to study the model in other regions, but also during other periods besides 2022. Thank you very much. This was our project, so now it's time for the questions.
Yeah, thank you very much for this insight and then the final results. So we saw the midterm webinar, so that's great to see the closing of the project. So are there any questions? So my colleague Olga is helping here.
Okay, thank you for your amazing presentation. The achievements have been very, very good. So I have a question. Can you elaborate more on what machine learning techniques have you been used to perform this statistical downscaling?
Yes. So Yes, for the regression we used gradient boosting.
Okay.
Yes, a gradient boosting regressor. We haven't tried other methods, but this one performed quite well, we think. And for the clustering, we used DBScan. So these were the two models that we employed.
Okay, good. It seems that the underestimations are corrected. This negative bias, yeah, good performance.
Okay, next question, please.
I was wondering, in the first part of the talk, you said how there's a limit to how much improvement you can see. I didn't quite get the reason for that. Could you just explain that in a few more words? That would be nice.
Yeah, so basically what I said is that we have some model uncertainty and observation uncertainty, and we cannot improve higher than that. Or at least we don't know if we actually are improving or not. So that's why there is this lower bound.
Okay, so you have information about the model uncertainty of CHEMS.
Well, actually, it's, so if we go to the slide here. So here, basically when you use the MQI, you have this UOI squared, that's the uncertainty, and it's another formula that the MQI standard gives you. So this gives you the uncertainty of the measurements, for example.
Thanks.
Thank you.
Another question.
Hi, really great talk. 2 questions. What was the kind of feature importance of all the different data sets you used? Like, what were the key things that were driving the model? And then the second question, in Barcelona, there was kind of like a diagonal toward the lower bound of the city, just above the port, was it? Do you know what kind of caused that? Was there a feature there or something? Yeah, that one. So just the blue station, kind of like you can kind of see like a harsh boundary, almost diagonal. You know, it's like a bit of a shape, like a polygon.
So you mean this boundary?
Yeah,
the
yeah.
coastline.
So just above that blue dot. Yeah.
I think he means the polygon.
Yeah, you see where it's like almost
okay,
like rectangular.
those polygons.
Yeah, yeah.
Yeah. So I think those polygons can be clearly seen here in the first version, where we didn't use any extra data set. To get this map, we only use the CAMS and the EEA observational data. And we can see those polygons, which are in fact Thyssen polygons or Voronoi polygons, because the interpolation method of the observational data is nearest neighbors. So inside each polygon, we got the same value for this model feature, the observational data. So that's why each model behaves different, and we can see those limits. But as Adria said, by using other interpolation method, we can solve this problem. And you had another question.
Yeah, so on the feature importance, because you use a lot of different data sets, what was the kind of key things driving the model?
The most important data sets.
The most important. So I think this slide can answer your question quite well. We can see that when adding this population and road map is really when we can see at a street or neighborhood level how the different areas of the city have different NO2 concentrations. When using only the topography, we can use a better result, but we couldn't say that this is a urban resolution map. Okay, so I think that it's when using the population density and also the road information when really this downscaling works at a urban resolution.
Okay, any other questions here? None, and we also don't have any questions online, but congratulations. So thank you again.
Thank you very much.
No, ma lui è lì.
Can you hear me? So
let me introduce you. So, yeah.
Turn the green one off.
Switch it off.
The handout, that's it. Now use the handout.
That was so sorry. I'm not multitasking, although we're supposed to be multitasking. We have the next presentation will be online, so let's see how this works. But I wanted to introduce now one of the mentors. That's Corwin. He is here, and Corwin, Angel, and Jonata were the mentors for the team on optimizing CDS API dataset retrievals, and we will have Andrei Koto and Catalin Ionut Alvu online, and I give the floor to you.
Hi. So many of you are familiar with the climate and atmosphere data stores. A part of those, but not everybody, is also familiar that there are some guidelines on how to do requests in these data stores. These guidelines concern the size of the request, the structure of the request, and also the frequency of the request. So this challenge, until recently, these guidelines were mainly a list of recommendations that users needed to follow. Some of them didn't, maybe because they were not aware of the guidelines in the first place. So this challenge is supposed to put these guidelines into code. So there are multiple facets of this problem, ranging from request sanitization, just eliminate obviously malformed requests, to putting together a request to do smart resubmissions. Let's say you are interested into data that is released on a daily basis, then you want to somehow make that automatic. Don't repeat the same work every day. And then there's also our main concern: don't make requests that are too large. So, and also don't make too many requests. So the Team 1, we have two teams that worked on this challenge. Team 1 created a wrapper on top of the CDS API client that's taking an initial request, however bad it is, and it tells it to fit these guidelines, especially regarding size and frequency. Team 2 handled the initial sanitization of the requests and prepared some tools to compose requests from the command line, and also had a go at automating smart resubmissions. So Team 1 is online, no?
Yes.
Yes. Just a tiny bit about Team 1. Catalin and Andrei, they come from Romania. They were undergrad students at the beginning of this challenge, but they graduated meanwhile. Okay, all the best.
Can you enable the screen sharing, please?
Okay, so hello everyone. I'm Andrei, and together with my colleague Catalin, we worked on a few optimizations for the CDS API data retrieval, which we want to show you today. So first, let's see why these optimizations are needed. So first, we would like to avoid requests that have as a response datasets that contain empty data, because those are just a burden on the system and are actually not useful, as they can be efficiently rebuilt locally by reuniting the composed request. To imagine this in a better way, we can think of it geometrically. A data set can be seen as a hypercube. Of course, it may contain empty spots because there are certain fields for which there are no measurements or that don't really make sense together. Also, for each of such hypercubes, there are subcubes, which are called constraints, and their properties that they don't contain empty spots. So yeah, we would like to make requests that don't contain empty spots and locally rebuild them such that we don't overload the system. And the second optimization that we worked on is regarding avoiding expensive requests. So of course, a very large request can be heavy on the systems. Users get penalized when they make such requests, as there are guidelines stating that these things should not be made. But the solution would be to make multiple smaller requests. This reduces the workload and ensures that users stick to the guidelines. Okay, so on the previous slide, I talked about constraints. This is how a constraints files looks like. So what does this mean? If you look at the source, you can see that there is soil, and for version, if we choose, for instance, version latest and variable nitrogen oxides, this is present in the constraint. So this means that we have data for this variable, so there is no empty spots. But if we were to choose, for instance, soil as source version 3.1 and variable nitrogen oxides, since this is not present in the constraints, there is no data available, so an empty spot appears. Now, in order to represent these constraints and work with them, we decided to use a dictionary of sets as a data structure. This is basically an unordered map or hash map, whatever you want to call it, which contains as these strings, so the name of the variable, and as values sets containing all the possible values. Now, let's talk about the first optimization more in detail. So how do we split a request to make sure that it doesn't contain any empty spots? Our first idea was to intersect the request with each and every constraint. Of course, since constraints have the property that they don't contain any empty spots, this would guarantee that the resulting set of sub-requests does not contain any empty spots. The problem with this is that the number of sub-requests is not minimal, and it can be actually very large for large constraints files. So then the second step was to reduce the number of sub-requests that result from this operation. We noticed that sub-requests can be reunited without creating empty spots if they differ by only one variable. And of course, this is very important. Order of merges matters. So if we decide to merge two sub-requests before another two, this might result in a different minimal set of sub-requests, and it will have an effect on the solution further on. Let's take a look at an example. So let's say that our initial request, we have the same constraints file that you previously saw. We have an initial request for source aviation and soil, version latest and 1.1, and variables nitrogen oxides and acetylene. After intersecting with each line in the constraints file, we get the following 3 sub-requests. And notice that the last 2 sub-requests can be merged together because they differ only in the version field. So after the reunion, we get those 2 sub-requests. This is the minimum number. We cannot merge this anymore because we would get empty spots. And after the reunion, if you look at the constraints file, with this sub-request, there are no empty spots. Okay, now making this reunion is not that trivial, mostly because, as I said previously, the order of the merges matters. So one of our first ideas was to use a backtracking strategy, which just tries to generate all or most reunions between sub-requests. One of the backtracking strategies relied on generating all the permutations and then reuniting them. But this, of course, is extremely slow. Then we tried another approach, which relied on generating connected components. So trying to draw an edge between 2 sub-requests, and that edge meant a union in them. This is faster because we can rule out some cases, but it doesn't try all the options. But still, it tries quite a lot of them. And of course, because of that, is still quite slow. Then we thought about some heuristics, and we came up with the maximal and minimal dimension reunion. Basically, we select the dimension after which the reunion is done, and it's either the one that yields the maximum size or the minimum size after the union. This, of course, is very fast because it doesn't try that many options. It just goes in the way that the algorithm has to. And because of that, it doesn't guarantee a minimum number of sub-requests. It's an heuristic after all. Yeah, and in order to figure out how good or bad these strategies are, we did some experiments. You can see in this table the results that we got. So overall, the best strategy was the heuristic with the maximal dimension strategy. You can see that it reduces quite a lot the size after the reunion, and also it is very fast compared to the others. The backtracking strategy, as expected, it's slow. This is the connected components one. And because it's the connected component one, of course, it doesn't yield necessarily the minimum result. So that's why in some cases the maximal dimension strategy returned a smaller result. Yeah, the minimal dimension strategy turned out to be quite bad. It's fast, but the number of requests doesn't get that small.
As previously mentioned, the user need to follow some guidelines in order to make the request small enough in order to not burden the server and get penalized for the big request. To fix the problem of large requests, we need to split the initial request in smaller sub-requests. And we do that by choosing a dimension after which the splitting is done. And we came up with 5 approaches to choose that dimension: splitting by the dimension with maximal size, splitting by the dimension with minimal size, splitting on a dimension order, splitting on a random dimension, and splitting on the dimension with maximal cost reduction. The new size of the dimension is calculated based on the current dimension size, the overall request cost, and the maximal request cost. The last two parameters are retrieved by default from CDS API, but in case custom costing function is needed or a custom maximal request cost value is needed, they can be passed to the request optimizer. Now the cost of a request is calculated by multiplying the sizes of all the dimension in the request. But we've came up with multiple approaches in case something to keep the solution flexible, and in case something changes in the future in how the cost is calculated, to be able to do the splitting in a performant way. Let's say, for example, in the future, maybe the cost will be calculated based on weights. The splitting on a dimension order would be the most suitable strategy. Here we have an example of a mock request with the cost 60 and the max cost 30. And the strategy chosen is dimension with maximal strategy. So we split by the year dimension. And as you can see, it will result in three sub-requests. Also, here we have the same request, but in this case we have max cost 11. As we can see, the first split is not enough. So the solution will split each sub-request from the first level again, this time by the day dimension. Our solution, the new CDS API client, is a wrapper over the current client, which performs some extra steps before making the requests. First, intersects the request with the constraints, unifies them to be sure that we have a more minimal number of sub-requests, and optimizes the expensive requests. And only after that, the requests are made in a traditional way using the current CDS API client. Also, our solution accepts some extra parameters, like the directory where the data to be saved, if the sub-request should be executed in parallel or not. The user also can select the strategies for both request unification and request splitting. And finally, the solution will output a log file containing all the sub-requests, the corresponding file, and the cost of the sub-request. In conclusion, we've implemented multiple strategies for both reunion and request splitting, and we've concluded that the maximal dimension strategy is the most effective, is the fastest, and is very effective for the reunion. The backtracking strategy being more accurate in theory, but is very slow. And for the request splitting, from our tests, the dimension with the maximal size was the best. And as for future work, a better logging system could be implemented, and also an integration with the solution from the other team would be a big plus. Now let's see it a bit in action. Here we have a request for CAMS Global Atmospheric Composition Forecast dataset from ADS. And the request contains variables, 8 variables, single and multi-level variables. Let's execute it in parallel. As we can see from the log file, we have 2 sub-requests. The first is for the multi-level variables, and the second one is for the single-level variables. And we have the corresponding files for each of the requests, sub-requests, and the cost. We can see the costs are 32 and 40. And after everything is done, we can make another request, setting the max cost to 30 just for demonstration purposes. As we can see now, we have 4 sub-requests, each one of them having the cost below 30. Thank you for your attention. Questions if you have.
If you don't mind, I would like to make a few additions. So they forgot to mention that everything is dynamically fetched from the new stores. So the forms and the constraints and so the definitions are dynamically fetched from the stores. So you don't need to be concerned as a user with all these aspects. So in theory, it should work as a CDS API, but just a wrapper on top of it. So, yeah.
Okay, thank you very much, Andrei.
Also, the maximum cost is fetched dynamically, so you don't need to set it yourself. It's fetched dynamically from the system. So, yeah.
Okay, thank you very much, Andrei and Katalin. Are there any questions from the audience right now? No questions here. Let me. Yeah, there is a question.
Hi, thanks. Just a quick question. I might have missed this. Was there an estimate of the reduction in burden on the system that this might help with or achieve?
No, we couldn't measure that now, but maybe some measurements would help to know that.
Yeah.
Other questions?
I will answer this question. So the initial request, if it has holes in it, is very easy to evaluate how effective the constraints intersection is. So selecting only valid data, that's very easy to assess. It's just multiplication and division in the end, calculating volumes and dividing by the total initial request volume. That's it. So that's very easy to evaluate. But in practice, I guess we would need to actually make this available for users. Of course, some more testing will be needed before that, but in case we make this available, it's only then when we'll be able to evaluate if this is improving and allowing the system to cope with higher loads or not.
Okay, if there are no more no more questions here the audience, I would like to go to the next presentation. Just another round of applause. And so we have a second project on the same challenge. And I would like to invite Irina Cukowerski and Tom Calloway to the stage. And Pedro is giving a short intro again.
Yeah. So same challenge, second part, concerned with the initial sanitization of the requests and preparing some tools to compose valid requests from the CLI, very similar to what the web interface is doing. So when you go on the website, you go to this data download form. So something resembling that very closely from the CLI. And then there is another part that we address, but it's not yet complete, I guess, the automating of smart resubmission. So in case you are interested into data that is released, let's say on a daily basis, just automatize as much as you can this process. Oh, nice to meet you in person.
Thanks, Richard.
All the best. Yeah, a short introduction on the team. Tom and Irina from Portugal, both software professionals.
Thank you. Yes, and we definitely felt at a more personal level the benefits of the center's atmospheric data, because in northern Portugal where we live, there's active fires at the moment, and so we were monitoring the air quality on a regular basis to decide whether to open the windows or keep them closed. And so we felt like the flight here was a bit of an emergency rescue. So. Yeah, that was a very interesting presentation from the previous team. And I did a quick queuing theory calculation based on an extrapolation based on some data a few months ago from the system. And it looks like at any given time, there can be 2,500 requests waiting for data requests, while 300 to 400 can be running at the time, leading to something like 100 requests per minute, maybe peak or average capacity. And each of those requests need to wait on average about 26 minutes. So there's significant amounts of time for waiting, for processing, and data involved. So any efficiency improvements there can definitely reduce the time for users, as well as the burden on ECMWF systems. So Irina and I worked together to achieve several deliverables related to handling dataset requests to the system. And we definitely want to thank Petrus and Janita and Angel for their help. So the main deliverables, as you might remember from the midterm report, were a validation capability. So since the requests are ultimately made through Python calls, we provide a Python library to do some validation. And I'll get into more details about that in later slides. Additionally, since the last presentation, we added a check for new data availability. So whatever the request was in the past, we can look at the latest data extent pulled from the API and then show what the next available date range would be for pulling data. And finally, something that took a lot of work in the last month or so was building a terminal-based, what I would call a request management system, where users, much like in the web interface, can go through a terminal-based application on their own computers to which also uses the API as well, just not a web interface, to create requests and also save them and resubmit them and more. Our work is in this repo, which I think will be made public soon. And this is just a refresher of what the web interface looks like. You might be familiar with this. There's a series of forms to define values for dimensions that you're interested in. And then that request is translated into Python code that can be run through a CDS API Python library, which already has existed for a while. And we also use that. I won't go over this too much. The other team covered the constraints. I'll just mention that there is also a form schema that defines what values are available for each dimension, and also has some additional details about UI concerns. And this is what the web interface relies on, and we also rely on this. So just going through the library functionality that we add, which is complementary to the CDS API package. Here is a request in Python. And we have a top-level API module called API. And so on that module, there's a function called validate request, which wraps up all the validation capabilities that we offer in separate functions into one function and summarizes whether the request was deemed valid or not. And when it's not valid, it shows details about why and where it's specifically not valid. And so we hope that will definitely help users do self-service and catch these problems, as well as help ECMWF support staff figure out what went wrong. An initial version of the validator, assuming strictly that only what was available in the form definitions for those widgets would be allowed. If you look at historical requests, I think 50% of the historical requests would have been invalidated. And the reason is there are a lot of exceptionals, behaviors and things that are allowed by the actual CDS engine that a strict interpretation by the form schema would actually disallow. So we incorporated a lot of those special cases, the ones that made sense. So it's still a relatively flexible validator, but built on a strict foundation. So the new function that we added in the last month or two was checking whether the request has new data in the next time window. That is, the time window beginning the day after the previous request ended, up to the latest temporal extent defined in the API for that data set, and if any exists. And so hopefully this would allow users to not resubmit a request and also use differential requests. And to that end, we have an early version of a function here that can modify the previous request to change its date range to use that next time window function. And then a user could resubmit a request for that next time window, which would be a much smaller request than their original one, rather than trying to do a combined range. Okay, so next I want to go over some of the new functionality in the terminal app called Request Composer. So this tool, the idea is to allow users to create valid requests in their terminal UI rather than the web browser. I'm not sure how much adoption this will have, but it was definitely fun to make. So they can define values for each of the dimensions, walking through step by step. And at each decision point for each dimension, values will be, due to the constraints, those will be applied, and some values will be disabled, just as in the web interface, some values are disabled due to your previous selections and the values of the constraints. Then after the user creates that request, it can be submitted to the CDS service, as well as saved locally to a database, which allows many possible things. So this will be a very basic interface. It is a terminal app after all. The first step is just to get the user's permission to show them where the database will be stored. It's a SQLite database, which is just a single file. And so after that, good, the animations work. These are GIFs. So each screen has a single purpose, each view. And this one is the main menu, which allows them to create a new request, or as we'll see later, look at previous requests. The next one allows the user to select the data catalog. So there are several data catalogs, ADS and CDS being some of the main ones, and I think there are a few additional ones that could be added over time. I should say that this app is based on a Python library called Textual. If you look up Textual or Textualize, you'll find that. Yes, okay, so this flow shows the possibility of selecting the catalog, and at that point you can also paste in a request, one of those Python requests, and run the validator. So you don't have to enter any Python yourself, you just paste something in and you can check the validity of the request. Otherwise, you can continue with the flow where you select the data set and go through the process of selecting each dimension, as you'll see here, to go through the flow of creating a full request. And we'll just kind of let this complete. I'll add that there are a few specialized widgets that are not supported yet. The area widget had a small problem, so we just disabled that for the time being. Okay, this should almost be complete. Okay, here you can submit the request. And you'll see a little bit of, oh, it doesn't show it. At that point, you would see a little bit of logging from the CDS API Python library as it submits the request. So it's a little bit of a progress indicator on your screen there. It might show that here, actually. Okay, it was very brief. Okay, there it is. And just as you can currently with the web interface, you'll see that requests that are submitted through this tool will be visible in the web interface. You can check the status, whether it's in progress or not, and then download it as well on completion. Since these requests are stored to the local database, you can, in our interface here, look at saved requests, and then there's keyboard commands that allow you to go to another view for a specific request to drill down into previous attempts to submit that request with some various data that you can scroll through here in this table to see if there are any submission errors or if it was successful. One limitation is it doesn't automatically refresh itself. That is possible through the textual API. It's just, it would take a little bit more work to implement that. So you might have to check back in a few minutes to see the status. There is the capability to resubmit a request, as I mentioned before, using some of those API functions that we added. The recalculation of the next time window and modification of a previous request is a little problematic because the dimensions for each data set can vary in how they specify time and date. And so having a comprehensive solution there would just take a little bit more extension. We cover some of the main year, month, day patterns that we saw in many of the data sets. Okay, so I mentioned a few of the limitations already. Some of the other issues you might see when using the request composer are if you haven't already accepted the license for a data set, you will see an error in the submission errors view, and you would have to probably go online and accept that in order to successfully submit a request. There are some other errors that are possible that can be visible there. Sometimes the remote download form is not available from the remote system, so you have to wait. And there's a little bit of a problem with the downloads. The async Python context that we're executing within might be involved in that. One of the libraries, there's an issue when using CDS API library to download, but it still has about a 67% success rate there, and you can always download it from the website. Yes, one other limitation is that the ADS catalog, some of the widgets needed for that require user inputs that have not been implemented yet. So there's a little bit of extension work to do there to more fully support the ADS datasets. But the good thing is that about 84% of the CDS datasets are fully supported, and that's, I think, roughly 90 or 100 datasets. Okay, so some future work would be to refactor some of the validation code. We kind of implemented that, especially for the special cases, on a little bit of an ad hoc basis. And at the end, it became more apparent that it would be useful to express the special cases as Boolean true-false facts that then could be used in the appropriate places in combination with each other to decide whether or not to apply a special case. That would have resulted in some cleaner code. And so there's an example started, but it's not fully refactored in the code base. So that would be one thing to follow up on. And it's also possible for the validations to cover more of the special cases that the CDS engine supports beyond the strict validation case. So for the Request Composer app, let's see. Yes, you can paste a request to run the validation, but it doesn't actually save that request and allow you to submit it like you can when you click through and select all the dimensions. So that might be a nice feature to have. And let's see, I mentioned a few of these already. Okay, we did attempt to include error modals. So in many websites, to get a status, sometimes a modal will pop up, like a little window that you can then dismiss after it gives you the information. The library that we use, the textual library, we implemented this, but there was a little problem getting it to fully work without interfering with the rest of the views, and so we kind of disabled that for now. But there's code in place, and that could be, corrected at a later time. And yes, and I mentioned also updating the views when new data arrives. That would probably be a nice feature to have. So in the end, our code base performs uniform exception handling and also conditional return results for success failure patterns. And so this was nice to be able to bubble up problems to the top for API calls or also for use within the app. one of the advantages, despite some of the work in progress and some remaining work to be done in the request composer, is a lot of the basic problems of the app were solved. We ran into a lot of issues with how things looked in the textual documentation versus how they worked in practice or interfered with each other, and we found some workarounds for that. And so that should save future maintainers some time so that they can just mainly focus on extending the basic functionality in very localized places within the code base. And there are some technical patterns also that will save some time and be conveniences for programmers. And I think this is the last slide. So in the end, this library provides value that could be incorporated into the CDS internal systems to screen requests at the beginning and give early feedback so that requests don't enter the system and have to wait until the end to know whether they were invalid or not. There is some of that logic already in place, but this might improve that logic. We expect this will reduce the number of issues reported by users and the time spent by ECMWF staff. And otherwise, without something like this, there is not a good way to have quick insight into the precise nature of request failures and how to fix them. And so this provides a solution for that. And also, with the other team's work, it would be definitely a great idea, like they said, to integrate this, to take the initial request and then split it into many requests that then could be saved to the local database, and these requests could then be managed over time. So I want to thank Irina, my co-partner on this, and we spent a lot of time together working on this project and doing lots of QA, and it was very fun. So thank you again.
Thank you, Tom. Appreciate it. Thanks to Irina. Are there any questions? Angel, wait.
Yeah, thank you. I think it's very interesting what you have done in this and in the previous challenge. So I think it provides us with a lot of inputs that we can consider for the evolution of the thing. I'm quite interested about the statistics that you presented about how all these solutions may impact in the performance of the system and thing. And I think it's related with your previous question. So more than a question, I think is a comment that probably we need to interact, because we are in this transition period now from one system to another. So probably there will be some deviation in the stats as we are moving. It's a kind of migration. But I would like to discuss with you later, probably, or more in detail, how we can evaluate these stats and the numbers.
So if you mean, since the CDS beta service is in place now, if that's what you're referring to, we did have a QA script. Patrice provided a data dump in a CSV that we were able to import and create a script for to run our validator over those previous requests from and point our APIs to the servers, the hosts for the previous version of CDS. And then we also ran those same historical requests pointing instead to the CDS beta API. And so we actually had the same validation results when applying the new form and constraints that are available. So there might be some problems, but I expect maybe there would be fewer than might be expected. There seems to be a lot of agreement between the two systems. But maybe there's more nuance to your comment there, and we could talk about it more.
Yeah. Okay. Thank you.
Mm-hmm.
Any other questions? I'm checking for online. Don't see any online questions. Okay. Thanks a lot. And then I would like to, so first of all, thanks a lot for all the speakers to keep the time. And so our colleague Jörn Hoffmann arrived. So can you please switch back the presentation to Jörn's, the slides to Jörn's? Jörn is our team lead, and he has an oversight over Code for Earth. You were delayed due to traffic, but yeah, now we're putting up the slides for you. and then you
Can I
can.
move
Yeah, you move as that. You want that one?
I think
You
this
have it.
should
Okay,
work.
perfect.
I'll try that. Okay, good morning, first of all. Thanks, Athena, for the introduction. Yeah, apologies for being late and sort of mixing up your schedule a little bit. Again, my name is Jon Hoffmann. I'm the team lead for Applications and Innovation Partnerships at ECMWF. And my role here is, to tell you a little bit about ECMWF, maybe to motivate also why you're here. You found your way here, obviously, and I noticed that Tom even managed to say ECMWF without breaking his tongue, which is not something that many people accomplish at first sight. But you have been working for a few months now, coding on topics that touch our work, and now I wanted to give you a brief overview of who we are, what we do, and why we're implementing a program like Code for Earth. So first of all, ECMWF has been around for almost 50 years. We're celebrating our 50th birthday next year. Up until a couple of years ago, there was only Reading as the only site. Since then, we've become a 3-site organization with the other sites in Bonn and Bologna. Some of you may have been to one of the two. And we have 2 roles, really. We're doing operational forecasts, medium range, that's up to 14 days in advance to serve national Met services. And we're doing research on a range of topics related to modeling the Earth system, particularly atmospheric and ocean parts. So the idea, why you might ask, is this an intergovernmental organization rather than just a research center? And the reason is that this involves very heavy computational tasks in particular, but really challenges that none of the national Met services was able to do alone when ECMWF was founded. And we've evolved, of course. The challenges have evolved. What we started with 50 years ago, of course, could be done by almost anyone today alone, but of course we've moved on, and some of our more groundbreaking work we're doing today, again, touches, really pushes the limits of what's possible technically, but also scientifically. The headquarters here is in Reading, and this is where you are, and the Earth system that we're talking about, I think many of you may have a meteorological background. It sort of motivates the getting in touch with Code for Earth. But just to recap, it does have different physical components, all of which interact and are coupled through different processes. So the land, the ocean, the cryosphere, so the ice bodies, and which one did I miss? The atmosphere, I think. And they're all interactions with them. These are very complex and chaotic systems, so modeling those is not an easy feat. And up until very recently, this has been basically very large physical models that were implemented on supercomputers, essentially. And one of those supercomputers is managed and operated by ECMWF, and it's located in Bologna. But in the last couple of years, of course, artificial intelligence applications have gotten a boost, really, and so this is still running on supercomputers, but some of those can be run on smaller machines also. Nevertheless, that's what we're engaging in. All of these processes are simulated and investigated here. A very important element of making this all possible is observations. These are sourced from a huge number of instruments, 800 million observations, individual observations daily that go into these models to constrain and initiate them. They're from buoys, from airplanes, from atmospheric measurements, of course, on stations that you see all around. Satellites play a very important role, especially in coming up to that very big number, but they also provide a global perspective, which is really important in getting the constraining the simulations at the global level while the in situ observations are usually clustered around closer to where people are. So these are covering different aspects, and they're assimilated and integrated into the modeling system. And that's also one of the important research and operational tasks is ensuring this operation. The output is very different. It's not just the weather. It also relates to a lot of the impact sector, and more recently, of course, it does link to the climate aspects. Many of you have worked on what we do in the climate change service, for example, which is including similar types of modeling on different time scales, which of course also includes different physical and statistical processes. What do we produce? This is sort of a range of the weather prediction products that we have, the medium range forecast, the typical weather parameters up to 2 weeks, the extended range, that's up to 6 weeks ahead, and seasonal, that's up to 7 months ahead. They're similar in the sense that they predict temperatures, precipitation, and the like, but of course accuracies vary vastly. In the 2-week range, you probably have most personal experience with what to expect, and the reliability depends a bit on where you are and how stable the weather patterns are. Up to the longer time periods are probably not reliable in the sense that you would plan your vacation on it, but for applications like agricultural planning, for example, this becomes relevant or for risk management, this becomes relevant because people, even though the reliabilities are lower or predictability essentially is lower than for the shorter term, it does add value. Environmental monitoring, it's not just weather, it's climate parameters that we are producing, atmospheric composition forecasts, smog, for example, ozone, in terms of health, but also, of course, in terms of ozone holes. These are products that we have added over the past decades to our portfolio. Another example is hydrological forecasts. Last week, this was a prime example, of course. Weather really stops at the precipitation, but this is the key input to hydrological forecasts, so river flow, floods, soil moisture, agricultural things. This is also products that we are providing. And another one that's more recent is wildfire risk, which again is very closely linked to weather parameters, but you integrate them over time and you combine them with other data in terms of biomass, fuel for wildfire, and the possibility for ignition. We're both doing the risk estimate, and we're also doing monitoring the parameters and simulating how, for example, wildfire smoke distributes. A lot of this is happening inside the Copernicus program, which is a large Earth observation program funded and managed by the European Commission, involving satellites, observations, but also a number of so-called core services. ECMWF is responsible for managing 2 of them, the Climate Change Service and the Atmosphere Service. And both of these provide operationally products, one on the climate change, climate parameters, climate indicators, and one on atmospheric composition. We also have a little part in the Emergency Management Service, which is managed by the Joint Research Center of the European Commission, where we provide input, for example, to flood risk. So this has been going on for a long time. Copernicus is almost 20 years old now, ECMWF from the start has been responsible for those 2 services. The Emergency Management Service contribution is a bit more recent. Here is one example from the CAMS, Copernicus Atmospheric Monitoring Service. This is one of the products, so organic matter distribution, and as you may imagine, these models were things that we already had, and added onto in the context of Copernicus, and we're providing these data globally for users to pick up from the service. Climate Change Service has different products, and many of you may be aware again. So it has the observations, of course, that are made available through our data store. We provide reanalysis, that's basically the perfect hindcast in a way. So the physically consistent, spatially complete representation of all data sets that were observed, even where they were not observed. In a sense, a very clever interpolation, if you may. My colleagues will probably kill me for simplifying it like that, but I like to think of it like that. And then the seasonal and decadal projection and climate projections. So these are the product lines that are in the Climate Change Service. We also produce reports, regular reports. This is something that's very much facing towards politicians, the general public. It's something that the media really likes to pick up. So it's annual reports looking back at the previous year and producing key highlights, like, it was a very dry year, there were a lot of wildfires, it was hotter, wetter, drier than the previous year in certain regions. So these kind of headline news that are really often picked up by mainstream media and that many of you may have seen, this is where they come from. And a new kid on the block, really, we started on this about 2 years ago, is the Destination Earth initiative, again funded by the European Commission, building a digital twin of the Earth. This really moves again to the cutting edge of what is currently possible with global models on the climate timescales and on the weather timescales, moving to higher resolutions, and also investing a lot of effort in making these models more interoperable, more interactive, so that users can really couple their individual applications much more closely than previously possible with these models. So they can run alongside the climate simulations, for example, where CMIP, the climate intercomparison models, have on the order of 100 kilometer spatial resolution. Destination Earth looks at 5 kilometer spatial resolution, which is really a domain where you're then starting to see differences at a spatial scale where applications really make a difference. This is, again, something that we just started working on. The objective is by the end of the decade to have a fully functional system that will actually be in use. We've just started the second phase of this program, so the data is now ready and available to users starting next month, and it will evolve substantially. So there's still a lot of things that will continue to evolve in co-design with different user applications. That's it, what I wanted to say. You're here at the heart of things, so I hope that you'll have the opportunity to talk to a lot of colleagues, to touch and investigate a bit further on many of the aspects that I introduced. We'll also be around for the 2 days here, so happy to have you here, and I'm really excited to listen to your presentations over the rest of the day.
Okay, thank you very much, Jörn. And I say that's perfect timing for the coffee break. So the coffee break it will be in the lobby and the weather room, where we met also, where you came in this morning. Use the time to connect with people. There are colleagues here. I also see a colleague, an ECMWF colleague who was a participant in Code for Earth. Yes, Nico, so he's in the back. And at 11 o'clock, we'll meet outside for the group picture. And then, yeah, have a nice break. And we resume at 11:15. Thank you. So, welcome back after the coffee break. Did we lose some people? I don't know. Good. Yeah, the next session, the session before lunch, is we collected or we dedicated it to the machine learning or more machine learning oriented projects And this is where, I want to thank again IFAP. As I mentioned in the morning, they weren't able to join. But I encourage everyone to have a look what IFAP is doing, because they have also a lot of projects relevant for our community. And I think it's a good source of information and potential project work. So IFAP Foundation in Bologna. And with that, I would like to invite Baudouin. He's one of the mentors of the next presentation. So they will be online, and I'm looking at my team in the cockpit. They will, okay, things are moving.
Okay.
Baudouin?
All right. Okay, thanks. So a year ago, at SMWF, we started to look into a large language model. I mean, ChatGPT. Yes? Hello, hello? Yeah, okay. So I'll start again. So last year we started to look into large language model to see how we could use it at SMWF. So we had two applications. The first one is to look up documentation, which could also be technical documentation. So like, how do I create an account on the CDS, or when did Georgia join ECMWF? So all sorts of documentation available on the web. And then also how to use it to create products. So you can ask, what's the weather for tomorrow, or what's the, give me an EPS gram for Toulouse. So this next presentation by a group of people from Vietnam was to extend the AI, the robot, based on the knowledge graph. So I don't know if you're online. So Duc Ayen, sorry if I don't say your name properly, Min, An, and Viet, worked for 3 months on trying to expand on the AI and add the graph knowledge to it to help the user navigate the question more efficiently. Okay, I will give you the floor.
Okay, thank you very much. Do you hear me quite well?
Yes.
Okay, thank you very much. So thank you for the gentle introduction. I would like to share my screen. Okay, do you see my screen? Sorry, do you see my screen? No.
Yes, I see it now.
Okay. Okay. Have you already seen the screen at the moment?
Yes, I can see it.
Okay. Okay, I would like to start right now. So thank you a lot for the gentle introduction. So my name is Viet, and right now I'm from Luxembourg, and my friends and colleagues here, they are from France. The project we are working in the last couple of months during the Code Forward challenge is how to apply knowledge graph to enhance large language model and scientific literature synthesis. So to give a little bit context, because large language model took the world by storm like in 2 years ago, and since then people have tried to find the application of large language model on everything, and also they want to apply the existing technology on large language model to enhance its performance and trustworthiness. So one of such tool is the knowledge graph, and this is the main focus of our work. Okay, so to give you a little bit of what will be on today, this is agenda. We start with the problem description and a solution. Next is the our approach, how we conduct the work, and next would be the demo, small demo of what we have done, and later is some future direction. For that, I would leave it to my colleague to start the first part.
Thank you, Việt. Yes, so first I will present about our problem. About our problem. So for the background, ECMWF has already deployed an online chatbot, so with which we can ask about anything, but especially question about meteorological and weather forecast information. So basically, we give the question, and the chatbot will answer us in text, image, or also code. So the technology behind this chatbot is ChatGPT, so which is a large language model. So large language model usually suffer from hallucination. So next slide, please. Yeah, so normally large language model usually suffer from hallucination and knowledge cutoff. So which means that the answer may not be 100% correct, and the chatbot's knowledge will be limited to some point. So to solve these problems, we can inject more knowledge to the chatbot by using knowledge graph. So next, please. Yeah, so knowledge graph is a structured data storage which contains entity in real life as nodes and the relation between them as edge. So basically, it integrates knowledge into a graph as a storage. So you can see the image in the right. Next, please. Sorry. So for our project this year, the goal is to enhance the chatbots of the ECMWF in two means. So firstly, from the meteorological and weather forecast documents, we will create a knowledge graph based on them. So this knowledge graph will serve as a knowledge base which help the chatbot to reduce hallucination and improve correctness of the answer. So secondly, a small interactive knowledge graph will be generated beside each answer of the chatbot in order to visualize and provide better comprehension of the answer. So that are our two main goals in this project. Next slide, please. Yeah, so now we have several solutions, and the two foremost solution would be, one is a large language model graph builder. So it is developed by Neo4j. So Neo4j is a graph and a database technology, and this package is has friendly user interface, and they store knowledge in cloud. And the second solution is the GraphRap developed by Microsoft. So they have no idea of they have the community description on the entity, and they have the description on this entity community to summarize the entity. But the problem that they are very heavy and they don't have visualization. So now my teammate will discuss about our approach in this project. Okay, so now we are going to the details of our approach. So first, I'll give you the overview of the whole architecture design, and then we'll go into details into each component in this architecture. So next slide, please. Okay, so first we will have the documents and the knowledge resources, and they are available in the PDF files. And now we need to use a knowledge graph generator to extract, to process these PDF files and extract the knowledge graph or any other necessary information into JSON files, and these JSON files will be uploaded to Neo4j, which is a graph database, as we just mentioned later. So and
And this Neo4j database will work with the Python, with a Python backend, which finally interact with the front end that is written in React. Okay. So first, about the knowledge graph generator or knowledge extractions, we first need to process these raw data, which are available in PDFs. So first, our work is to extract the text, the raw text from these PDF files. And while doing so, we have to pay attention to some details. For example, we have tables and figures that are not extractable, but still we have some captions of those figure and tables extracted to the text file. So we have to pay attention to that. And also there are some parts where the text is very repetitive and not useful for the knowledge. For example, the footnote or the or sometimes the headings are not quite enough useful. So we also ignore that in the text files. And from that, when we have the text files, we can use a large language model such as ChatGPT to extract the knowledge graphs and other information such as the text chunk and such as the content, the chunk content and the embeddings, and this will be explained in the next slides. But for now, we now have the knowledge graph, which is included, which includes the entities and relationships, and also the text chunk. So now in the next slide, please. So now we need a Neo4j to store those data. And Neo4j, as I mentioned, is a graph database. Is very famous for storage of knowledge graphs, and it has some emerging techniques to work with the AI chatbot. So that's why we choose Neo4j for our database framework. So next, my colleague Viet will present to you the rest of our work.
Okay, so to explain more deeply what we have done, so we start with an example. So for example, here is a sentence we extract from the document. So here's the physical fluxes are archived by the ICMWF model, and from this one we extract two entities. The first one is ICMWF model, and the second is physical fluxes. And these two entities, information is stored in these nodes in the graph database. So first we have the sentence which is stored in the chunk, and second is the entities that is stored in the entity extracted is going to be stored in the entity nodes. And these two node is linked to each other by the relationship appeared in. Now we have like graph of entities, right? So we need to so we try to cluster this entity together, and so with this clustering step is kind of like to give us a little bit of global view of the document, rather than just process document by text chunk. Right now we can have some level of globalness of the document. So at the moment, I would like to emphasize that we have three types of nodes. The first one is chunks, and the second is entities, and the last one is communities. And all three types of chunks, nodes have embeddings. So this is for facilitating the search later. So now we have information like next we have to find a way to retrieve information. So we start. So when users type their query, their question, from that we also have chat history. We from the local point of view, we're gonna retrieve the relevant entities, and From these relevant entities, we can retrieve the relevant chunks and relevant communities. Chunk have contents and community has some summary. So, and we collect all of the content and summaries and chat history, and we put it into context. And this context want to be used to provide to LLM later. The second type of retrieval mechanism is global retriever. So we start with user query and chat history, and we search for the most relevant summary. So we attack to the more global view, and this summary gonna be provided as context to LLM. So this retrieval mechanism is greatly inspired by the work of GraphRag of Microsoft. Okay, so right now we have the whole mechanism, and next we have to find a way to visualize this and incorporate in the chatbot. For that, we use web application. We have backend as a Flash application, front end in form of React application. Okay, so the workflow of the graph would be like this. So first we start with a query, a question from user, and this one gonna start the search process. The search process appear in database, and the database gonna retrieve relevant information from the all the contents and also the graph. And this all the information is returned back to the web interface. And from that, we split out two results. The first one is the answers, and the second is the visualization. So I would like to show a little bit of demo of the web app we have developed. So you can build this web app from our GitHub repository by using the Docker file. So here we can start with the chat. We can start. So right now we only integrate the chat app and ignore the part of constructing graph because it takes some time. So for the sake of time, I just present the result in the chat app. So we can start typing what is the main idea of the document, and it will present first the question for the answer, and the answer is incorporate all the information in the entity. It can be entity, it can be some community. We have this community here. It's also information of the community, and the text chunk have the information of the text chunk. Chunk here have a contents like that. So all of this information is fed into the LLM, so it can have some knowledge relevant to the question and start giving the answer. Okay. So this is still a very early work, and we face a lot of difficulty during the project, and it's also the opportunity to develop later. So the first one is prompt engineering. So to give the instruction for LLM to extract information from document is because right now we focus on the ICMWF document, and sometimes it requires some domain expertise on this one to give the fine instruction, and this is not easy to acquire. So to construct a good prompt is difficult. The next is the unpredictability of LLMs. So if you give the instruction of LLM to do stuff, to extract information, and in a large document that might give that might lead to some unpredictability of the result, and sometimes it's difficult to assess the quality of the extracted data set. And next is because we at the moment we use ChatGPT API, and there's some limit on the number of code to construct the database. So if the database is very long, we cannot accelerate it through multi-thread because the number of code is limited. Okay, and next is the visualization. So as we can see, the visualization is in a very simple form, and we can find a different way and more beautiful way to present a more intuitive and result for the user. Next, I would present some future direction that we can take. So the first one is enhance the entity extraction. So as we can see from the prompt engineering, we do not have good prompts. So sometimes the entity return is not very good. Sometimes the entity, they have the same entity, but is written a bit differently, and that is a part that we have to merge these two entities together. Next is how we can enhance the graph in construction. So we might consider using local LM because it doesn't cost much as buying coding API, and we can use multi-thread to accelerate the graph construction. We can extend the local retrieval. So before that we only see the retrieval operate on the node level. So it also can operate on the edge level also. So it is another way to retrieve more information from local point of view. And next is to enhance the visualization. Okay, so thank you a lot for your attention. I'm happy to take your questions.
Thank you very much, Yet and team. Are there any questions from the audience here? Yes, there are questions.
Very interesting project. One question: did you manage to try a local LLM?
We try local LLM, but my first impression is that sometimes it's not as fast as by calling direct API, and it's a little bit contradicting to what I said before. But because if we can manage to use a multi-thread, maybe that will be faster. We worked with the local LLM before, but we switched to the OpenAI API because it have greater support from the from libraries such as LangChain and LlamaIndex and Neo4j also.
Yeah, also like to add that we used to use the Llama 2 model in the local GPU for experimenting, but the problem, as we said, that we have some problems with the precision, with the accuracy of the extracted knowledge graph. So that's why we move on to ChatGPT, and also ChatGPT has some faster processing. So yeah, that's why we stick to ChatGPT in the last of our work.
Okay, thank you. Other questions from the audience here? None, and we do not have any questions online. So thank you again for joining online. And another round of applause. Thank you.
Thank you very much for the
So
Thank you.
Then we move on to the next project, which will be in person. It's the project Polly, and the goal is to assist the extraction of complex weather information for users by both technical and non-technical users. So Christopher, Nadia, Kathleen. And we have also the mentors here, Adam and Matilda. So the floor is yours. You want that one?
Sure.
Yeah, just
So, yeah, okay. And how do you... I guess I'll get us started while we figure out the other mics. Yeah, so me and Matilda are the mentors for this project. We're in the Data Infrastructure Services team at ECMWF. We work on basically Polytope, which is a data retrieval API that is works on our operational data, but increasingly it's also used for Destination Earth as part of the digital twin engine. So it's one of the components that we create. And obviously for operational data, a lot of it's used by Met Services and maybe more expert users. But for Destination Earth, there's probably being a larger audience, a wider audience, maybe policymakers, maybe just citizens from the European Union who maybe aren't as used to accessing data, or maybe aren't as technical. So what we're working on is Polytope feature extraction, which instead of retrieving the global fields like you do in Mars or currently in Polytope, you just retrieve certain features like, say, a time series, a bounding box. You can put in a shapefile if you want the region of a country, say, or a NUTS region. But even still, that's quite complicated for just somebody who's not used to this type of thing. So we had the idea of creating a chatbot, basically, that would be able to aid users. They could put in a natural language query, and then that would convert it into a Polytope feature extraction request, which then they could use to retrieve the data. And I think it would just be a nice thing to have maybe for more outreach and interaction with Destination Earth and digital twins, and also our operational data as well. So I'll hand over to the guys. So it's Nadia, Caitlin, and Clive. They just finished their masters successfully, and they're starting their PhD at the University of Newcastle. And I think they've created something quite nice and done some nice research. So I'll hand it over to you guys. Thanks.
We are Project Polly, and our project looked at using a natural language processing interface to extract complex features from weather data cubes. So here you can see our names, Clive, Caitlin, Nadia, and our PhD projects. Now moving on to the motivation.
So in order to access and retrieve data from the ECMWF, you can either access via the Copernicus for free public available datasets. You can also access via an API for non-public datasets, or if you're a member, you can access it via the ECMWF website. So this further highlights how challenging it can be to extract and retrieve data directly from the ECMWF. But what about unfamiliar users? What about users who don't know anything about the weather domain? So we asked here ChatGPT to retrieve some data for us, and it came out with a Python code that might not be easy to comprehend for people who don't know how to code. So more specifically, how can a non-familiar user extract time series, 2D cutouts, shapefiles directly from the ECMWF dataset? This then further sets our objectives. So our main aim is to create a chatbot that can retrieve data from Polytope. And then as a second goal, it would be nice to have a web user interface, easy for users to interact with and then easily retrieve data. But first, we need to understand how is this data managed and how is it organized, right? So we have MARS, which stands for the Meteorological Archival and Retrieval System. It's the data management system designed by the ECMWF to store and retrieve meteorological data. This system supports a wide range of data that optimizes high performance data access. But how do we only access the data we want? So here comes Polytope. So for each data set within MARS is composed of multiple data cubes. However, the user doesn't want the whole data cube, as it's a large data set. So then Polytop allows to handle complex queries and massive data sets efficiently, and only extract the data that the user wants.
Now on to the background. So an LLM is a type of natural language processor. I'm sure you all know this. We can use it to respond in a human-like manner. So what is RAG? RAG stands for Retrieval Augmented Generation. It can be used to improve the accuracy and the reliability of AI. We use the documentation from the Mars for the RAG to use. So instead of giving a weighted answer, the AI will first look at the documents that it's been given.
So we've explored different, let's say, aspects of this project. We first explored fine-tuning. Fine-tuning is just the process of adapting a pre-trained data set, pre-trained model to a specific user case. However, like fine-tuning can be very efficient for simpler tasks. We did manage to come into a few challenges, especially because the volume of the data is big and it's complex to just fine-tune it. So given these challenges, as a team, we decided to not follow fine-tuning and maybe leverage pre-trained models with advanced prompt engineering, as many of you might know, with the launch of ChatGPT. So what are the components of LLMs? We're here specifically talking about agents, which are just the evolution of prompt recipes. They can be very useful and simple to use, depending on your task. However, we did run into a few debugging and integrating challenges, as well as we did deem that it was not cost efficient at all. So here, one more, sorry. So here we could see that an LLM agent is made from 3 components: the LLM, which selects the right action in a given situation; the agent's memory of previous messages and results is the state of the LLM; and finally, the tools, which is the agent's ability to interact with the external world or the user. However, the main limitation of these agents is that there is no standard approach and they're quite manual to set up. And here we just have a few agent frameworks that could be of use to many of you, or maybe you have already interacted with these in the past.
Okay, can you hear me? Maybe I'll use the microphone. How's that? No, I'll use the microphone. Okay, so just very quickly to demonstrate and kind of let you know how we are trying to essentially get this request. So we use, obviously you need to use JavaScript object notation, so it's a hash map or an associative array if you use that. So you essentially have a set of unique keys and a set of values that this is what we're trying to generate from the user prompt. So maybe they say, I want the weather forecast data for Germany. So how would we turn that into kind of this structure? Next slide. Yeah, and then it's an interesting one. At the start of this project, some of the tools available weren't available, and we'll come to that in a minute. But one of the things that was quite useful is essentially testing out your prompts and trying to add in your own prompts and kind of enhance what the user's trying to get from the model. You might have seen from some of the newer models on OpenAI, it's sometimes, especially nowadays, if you use the most recent one, you'll see it has that little section where it's trying to think, and this is that chain of thought process that's going on. So essentially what they're doing, they're getting one output from the LLM, thinking about it, using that as an input, and then trying to refine and make a better answer. So that's why you see the models improving at such a rapid pace, because it's essentially just retesting its answer. Okay, and I'll very quickly go over this. So prompt engineering is super useful. Kind of one of the points that was touched on earlier was the kind of that user expert knowledge, the subject matter expert. That really helps, because if you know exactly, if you can, essentially, it's as powerful as you are, it's as good as you can make it. This is good, but it's also bad, because then, you kind of get bias. Not everyone can use the models in the same way, so that's kind of where, that comes in. And kind of the unknown, this is that prompt engineering, so it's also an attack vector. So you might have seen some LLMs that are able to generate API keys, or they're able to get past the kind of safety measures, and it can do the things that we don't really want these LLMs to do. So that's kind of one negative of that. Okay, on these prompt models, so there's an example here. It's a very simplified example, but essentially all we're trying to do is say, ChatGPT, is the weather good today in my area or is it not good? And you can see the response here is not too useful and it's not structured in the way we need it. We need it to feed into another model. For example, maybe this goes to a web front end and it shows a nice big red flag or green sunny day, if it's a good thing. Here you can see the model is not able to pass that answer until we see here. The way you'd get around this is you'd feed in a system prompt. So you wouldn't just use what the user has said. You would give the system a way to kind of understand and interpret the data. So the forecast could be an API call. It gets the weather around the area. And then with your system prompt, you can say, OK, in general, if it's this temperature, then it's probably an OK day. As long as it's not raining, then you can say, yeah, the weather's good for a picnic. And then this is a graph that I showed in the last call. Big red X I've added to that because essentially the way the models are working now, they're getting better. And the way that you would in the past, when we first started this project, you almost had to beg the model to please output JSON in a correct format. And if you didn't, it had to kind of retry and test again. Nowadays, you'll see later, I'll introduce something where they are getting much better, and a lot of this is automated now. So yeah, getting LLMs to output JSON. As I say, some of this is out of date almost. But this blog post, if you read that, that's probably the best place to go. The benefits of using JSON is that you can use that in Python functions. You can use it in anywhere, really. It's interoperable. You can kind of move it around. So it's not just for the LLM to get your request for ECMWF. It's also a way for the LLM to be able to use those tools and go around that. And then, yeah, this is quite an important part, I think, and it's especially true now, that good LLM validation, it's just good validation. So if you know exactly what you're after, the object that you're trying to feed into a function, for example, the way you need to do that is just define it well and specify exactly what you need. At the start of this project, it could use this. There was JSON mode. It was available, but it wouldn't follow the schema strictly. So, for example, if you see this user detail model, it's a pedantic class, which we'll go into later. There's a name, which is a string, and an age, which is an integer. Previously, it might not get the string and integer bit correct, even if you use the JSON mode from a year ago. Nowadays, with some of the tools that OpenAI is producing, it can do that validation with the first API call.
Moving on to implementations.
Sorry. Yeah, so we actually, it's quite an exploratory project. Over the course of the actual project, things changed. The ways you kind of use these tools changed. And some of the things I won't mention, but I just want to briefly talk about if you want to talk to me during the break. So essentially those agent frameworks that we mentioned, function calling, so essentially letting the LLM decide how to use different tools. Alternative models, which was touched on earlier. So Llama is this very promising model. It's locally run, so it can be a lot cheaper if you've got some infrastructure there. Fine-tuning, very useful for this use case, but kind of need some sample data for that. And then I guess the DevOps side, some of the ECMWF tools and the tech stacks, they can be quite complex to get started with and kind of integrate. So that's where you kind of want this DevOps side and maybe have a very easy to use shareable environment. But we'll just quickly talk about that. And then, yeah, our approach at the entire project was essentially to mimic what you are used to using with these chatbots, OpenAI, for example, and essentially just hide all the complexity from the user because they don't need to see that. And that's where this kind of architecture comes in, the front end and the back end. The front end is the bit you're all used to with any chatbot. You just talk to it, you get an answer. That gets sent back to the server. In our case, essentially what the chatbot can do is it can test and see if there is any missing information. If so, it'll feed back to the user and say, actually, you need to tell me this because I can't just guess. I was not thinking, but maybe, who knows. The next step is to just validate that JSON, make sure it's actually parsable by the machine, and then also kind of go one level deeper, which is that schema validation. All the types are correct, the values within certain bounds, and so on. At that point, you can send that request away to Polytope, the library which lets you really get that data efficiently. And then this bit in the red box, so that's the kind of nice to have. And some of the back-end parts we'll talk about later. We essentially have some of this, but integrating it and kind of making that into a product is quite difficult at the moment. And we'll talk about that in a second. So yeah, back-ends.
Here we can see the results of the RAG. You can see at the top we've asked it what is Mars, and at the bottom it's given the definition of Mars. This AI uses only the specific knowledge from the documentation we gave it, so it doesn't search the internet or anything.
One of the most important keys of the backend is validation. So after the chatbot has successfully generated a request, or if the user can handle the data and knows how to generate a request, it has to be validated, and for that we used Pydantic, which is a Python library. So we need to first understand that this generated request meets the schema. So for that, we used regular expression, like we could see on the image here. For an example, everyone knows that an email starts with a series of alphabets and numbers, and then you've got the @ and then you've got the local domain, and then the commercial domain. So that's what we were planning, like that's our main goal. So for that, we have here the class Mars request, which has a nested Mars request feature class as well. And for example, we could see that the date, we have specified the schema of the day, so year, month, day, etc. This way we know exactly whether the request meets our regular expression.
Yeah, and then very quickly on the back-end side, even though this is essentially one of the foremost front ends you'd want to use, OpenWebUI is very useful as a back-end. You could actually just use the back-end. You don't even need to use the front end on this section. Why is it great? Because it's under active development and there's very extensible. So if you're going to build a large system, so you've got multiple components. So for example, integrating the previous talk's work, you'd probably want to have one user interface, and then all the complexity is hidden. And OpenWebUI is probably the best tool for that if you've got multiple services on the go. And then, yeah, as I mentioned previously, this is hot off the press, I guess, early August. OpenAI kind of introduced their structured outputs. They had JSON mode previously. What is structured outputs? Well, it's essentially just going that one level deeper, and it's really checking the schema is 100% valid. It's not just checking the keys and the values are roughly correct and there. It's also checking all the data types. It's checking if the values within the range you set, and hopefully in the future, not right now, it doesn't allow regexes directly, but you can imagine that's something they'll probably add quite soon and probably the way to go. So what did we use instead? We used Instructor. It's a library which is very useful, and it was probably the best choice, and probably still is the best choice to use when you're trying to generate these outputs. And you can see on this right-hand side there's an example. What is it doing? First of all, it's just testing if it makes the OpenAI request. It tests if it's valid, if there's anything wrong. It tries to fix anything small itself without having to incur an extra cost. And then you can see, if it has a big problem, it'll send another request to OpenAI and say, this is the problem I got, and can you please fix it? Front ends. So I think we can go over this bit quite quickly. So yeah, there's various front ends. Once you've got a backend set up, maybe a data scientist wants to use a Jupyter Notebook, and that's their workflow, and they'll use that request. You can see what essentially the example output. So you've got the user asks for something and gets the kind of request that they need, and then they can then use that to make that Polytope request. ChatGPT Builder, which we talked about previously in our other slides. So you can integrate this into this front end. It's one example. I'll just move on for that. And then another one, this one's very useful. It's quite a user-friendly one that Nadia found. I'm not sure if the video is going to play. But yeah, as I said before, OpenWebUI, this is probably the premier tool, and if you've got multiple components, probably use this. What do we use in the end? We use Streamlit. And you can see actually there's a map there as well, so it's not just the traditional chat interface. What we found was that LLMs, unless you really have a fine-tuned model, or you kind of go in depth, you provide a list of areas that are acceptable, it's not going to generate those well-known text polygons very well. So what's an alternative? Just draw it on a map. And probably the best, you want to use the correct tool for the right job, I guess. Future work. So yeah, if we knew what we know now, what would we do differently? So there's kind of three elements here. I'll just quickly go through them. So the separation of concerns. We've touched on a lot of different topics, but you can see we've kind of got the data retrieval from the ECMWF and the validation of that, the model tuning and selection as well. So using Llama, for example, as mentioned. The DevOps side was a task in itself, just trying to get all these components fitting together, especially the ECMWF, all the various libraries that are available. And then the front end, back end, making sure it's very reproducible and deployable on anyone's machine. That chat flow as well. I'll move on to limitations.
Okay, so throughout this project, we did explore different front ends, back ends. We've explored different methods, so that's why we feel like we've learned quite a lot from this. But there are a few limitations. Starting with like using different agents, different tools, different fine-tuning techniques, different prompts, actually give very different results as seen here on the plot. So also one limitation that might not seem like a limitation, but it's quite big, which is that models are constantly ongoing change. So we do produce something today and then the next day it's not working because they've developed a model and they've made it even like better, but like your prompt might not work correctly. And I would like also to highlight that the API was harder to implement, and we do feel like it's a bit premature to handle a chatbot for the moment, but we were still able to create something at the end, which might not be perfect, but still works really well.
We can see a sample request. So in future, in a perfect world, we'd have loads of previous requests that we can then use a chatbot to train on these requests and then fine-tune the model. But unfortunately, we just don't have access to that data.
Yep. And then very briefly, just kind of the key deliverables that you'll find on the GitHub page once that's open. So Project Poly itself, so you have a conversational assistant, which you can use to help you with those Mars Polytope requests. There's a Streamlit app where you can draw your polygon. That's probably useful in itself. You can probably just take out the component. So it's a TerraDraw, a very useful library, so you can kind of use that to create polygons for different use cases. The validation was a key one. Pydantic, very recommended. OpenAI, and also kind of this isn't really a deliverable, it's more of a comment, but just I think the local model is getting a lot better, so probably want to pay attention to, because obviously you don't need to pay as much money. There's notebooks and there's branches that are kind of looking to agents and frameworks that's available on the GitHub. And probably the key thing I'm quite proud of is kind of like GitHub code space, where we were able to just, because it was quite a difficult environment to set up, so if everyone do it on their own computer, everyone can have different problems, if we're using Windows or Mac and so on. So if everyone's on the same environment, it's quite a good little thing, and I think if you want to replicate that, it's quite easy to just copy that code. Thank you very much for your time.
So thanks a lot to the team, to the Project Poly team. Are there any questions? None? Maybe some from other teams that have been working on the ML parts. Let me check if there's something online. Yeah.
So is this planned to be a part of the ECMWF?
Wait, the microphone.
Yeah. Is it planned to be a part of the ECMWF platform or website?
Not right now. I think it's a bit too premature. I think the mentors have a good answer for that too.
Olga, Adam. Thank you.
No, I think this was more an exploratory project, and the guys have done a lot of really good research on that. I believe there's actually a tender going out for a chatbot as part of Destination Earth, so maybe they can use this as kind of some building blocks or starting points, but there will be at some point in the future a chatbot for access to not just Polytope, but I think some of other data access services via that tender.
Okay, there is a question here. Marina, can you raise your hand again? Thank you.
Hi, I saw that in your slide you didn't mention this approach, but I would like to know if you have considered the DSPI approach for this kind of problem, and why you haven't tested, if there is some specific reason, or simply you haven't.
Yeah, what's the acronym stand for, sorry?
DSPI is a new approach to programmatically query a large language model. I haven't tried yet, but I was curious if someone has.
I think, is that the one where it's essentially a very constrained, it's a model that's constrained with a grammar that you feed it?
Yeah.
Yeah, okay, we did look at that at the very start. The problem with that is it's quite complex, and as essentially the request was quite complex, to try and create that grammar was very difficult. But the very interesting approach to do that now is to use LLMs to generate that grammar, because then you essentially have that constrained on the JSON, you had all the values. You can constrain those values to a certain grammar, and you can only get those values. So it's probably especially useful for local LLMs, because then you're not having to incur the costs to go to OpenAI and get all that.
Okay, thank you.
Good. Okay, no more questions. Then another a round of applause for the team. Thank you very much. And with that, we are moving on to the next presentation. And we have Maliko presenting the mentors team. And Yanis Kontos will present. And we have also Kostas Plataridis and Kostas Perifanos. Yeah. And it's the HydroGap AI, and the goal is to apply machine learning solutions to data for hydrological analysis and decision making. You can have that. Wait, 1, 2, 3, 4, 5. No. Yeah.
Hello?
Yeah. That's for changing the.
Hello, so on behalf of all the mentors, I'd like to introduce the HydroGap AI team from Greece, represented here by Yanis and Kostas there from Greece, both from the University of Thessaloniki. So,
Aristotle, University of Thessaloniki.
Okay. So this project, which is looking at gap-filling hydrological data using machine learning-driven solutions, it was originally motivated by a problem we face when working with observational data and with hydroclimatic data. And it is that there's a lot of missing data. And for many applications, we need continuous observational data to be able to use that data. For example, calibration, forecast verification, or post-processing, a few examples. So we wanted to explore how machine learning could help us fill those gaps in observational time series. And we've been impressed by the work from the team, their ambition and their dedication, and I'm excited for them to present their work.
Thank you very much. Of course, we got you a bit anxious because we were always late, as we did today in the morning. So imagine that our last runs were last night. So our team is comprised by me, and I'm a civil engineer, doctor in water resources management. Kostas Plataridis is a geologist, actually a PhD candidate in our School of Civil Engineering in Aristotle University of Thessaloniki. We also have a board Konstantinos Perifanos, who is an AI expert. So we try to see this problem not from the machine learning black box problem direction, but also as hydrologists. The challenge is bridge gaps in stream flow observation using machine learning-driven solutions. The main goals are to investigate methods for gap-filling daily stream flow time series, evaluate effectiveness and identify the longest reliable gap fill for each model, which is something really difficult at this point, as I will tell you later, and develop a Python-based open source library for any end user to use when given discharge gapped, a gap time series of discharge, and total precipitation in a water basin. So there is the necessity for this research. We ourselves wanted for the digital twins, hydrological and hydraulic digital twins that we are creating in some current Horizon projects. We have a lot of missing data, so this is actually a necessity for us, and this challenge was a really big opportunity for us. So we have to address limitations in forecasting due to data scarcity and quality, which is actually the case in Greece at least. Ensure continuous time series for better prediction and evaluation, like the digital twins. Enhance water resources management, hydrological modeling, and support stakeholders. So when we try to see the literature, there's an absence of an open source library specifically designed to fill gaps in stream flow time series. Most of literature talks about rainfall or precipitation. There are really few. We have promised to write a review paper, and we tried to search for all papers in the field of gap filling in stream flow. There are less than 10. So we actually revised our title, and we are now also searching for, in our review paper, for precipitation data with gap filling. So there is a gap in gap filling of stream flows. So limited machine learning models have specifically applied for stream flow gap filling. Improvement of, we want to improve the predictive performance and integrate additional meteorological data such as temperature, evapotranspiration, DEM, land use, etc., which is actually a future research. We promised it, we couldn't do it in time. So we hope that we can continue to cooperate with ECMWF on that, because we actually need their supercomputer. And in heavily regulated streams, due to, let's say, dams, diversions, there is a low performance of gap filling and forecast models, so we want to address this problem too. So let's just see one example of our library, what it can do. We have a station of 1430 given to us, which is actually a dataset from GRDC. We have here an example of station 1355 in Brazil, which is actually that one. The GOES station is there. So we can see the total precipitation for this time range. So the GRDC dataset has this, only these range. We can see the stream flow time series, the respective, in the respective time range, and the red areas are the missing gaps. So I'm actually showing to you a really difficult example. The correlation of the total precipitation and the stream flow is like that. It is 0.467. It's one of the highest ones, which means that there are most of the examples are not like that. They're like 0.2 minus, which means that this river, at least at this section, is not heavily human, does not have a human altered flow, probably doesn't have dams or any diversions. So it's a good example. It should have some good results. So when we actually actually analyzing the data, the gap metrics, this is actually the first script in the first function of the library. We actually produce all the gap metrics. You can see here that the percent correlation is 0.67. The missing rate is 15% in the respective time range of missing data. Okay, this is the percentage of missing data. The number we have is 47 gaps, and a total of 1,676 gap days. It's a daily dataset. So here we can see the library actually, what it does is it analyzes the gaps, the characteristics of the gaps. It tries to introduce synthetic gaps with similar characteristics regarding the length of the gaps and the number of gaps and the total number of gap days. So you can see in black for the full range the actual values of stream flow, in red, which is actually overlapping the where you can see a red line. You can also see the black line because it's actually a prediction of the synthetic gaps. There we actually calculate the metrics. We do not have any split data sets or something like that. We actually introduce our own gaps with characteristics similar to the real ones. We calculate the metrics there, and the green lines are the predictions in the real gaps. Of course, we can never prove if this is a really good prediction. We can only assume that the synthetic gap filling gives us a good metric. So we can see in this example, we use all these metrics because at least, so there are the standard ones, let's say, there is the Nash-Sutcliffe, and all these ones, apart from the correlation coefficient, which is standard, Nash-Sutcliffe, index of agreement, and KGE are really something that hydrologists actually want to see. Okay, so this is actually a better aspect of the full, and we also plot in the library yearly plots so that you can see actually a little better the details. Believe me, this is a really good prediction because, as I am going to say, this was provided to us as quite a black box problem, only precipitation, and we have to find stream flow. It's really more complex than that. We would like to see the DEM, the elevation. We would like to see the temperature. We would like to see the whole hydrographic network. Is there a dam upstream? Is there a tributary river flowing in? Is there snow in the area? We don't know any of that. So these are really good predictions, actually. The red is actually the prediction in the synthetic gaps. The green is the prediction in the real gaps. I don't know if the colors are, you can see them really good. So we have some problems here. All models usually have problems in low stream flows because there is actually, the base flow is actually snow. We do not have the snow. And in the peaks. See, these are yearly plots of the predictions in this example. 2000. We're actually seeing an XGBoost model, okay, XGB. So, in this example, here we can see all the metrics for the 6 models that we use. Linear regression, not the plain one, but SDG regressor, stochastic regressor. The support vector regression, k-nearest neighbor, random forest, XGBoost, and LightGBoost. Here we can see the really computationally difficult run, which has hyper-optimization enabled, because in our goal was to provide guidelines for the full data set and some synthetic data sets with synthetic gaps, so that we can give guidelines to the user which models should he use or she use, depending on the characteristics of the gaps of his or her stream flow time series. We cannot do 10,000, almost like that, our runs was, with hyper-optimization enabled, because this needs some minutes, half an hour or an hour, so it's not possible. So under supercomputer of ECMW, I hope. So you can see here something that is not the most usual thing. We usually have random forest as the best, at least index of agreement value in the metrics, but here linear regression in the hyper-optimization enabled models, linear regression and KNN actually have the better results. So let's just see the materials and methods used. So we focus on efficient, reliable, and applicable methods. The library is tested on streamflow data by Global Runoff Data Center. Their datasets end at 2015. Probably it's a research project not funded, I think. Precipitation data by ERA5, average for each catchment. So this is a real big problem up front. We have average in the sub-basin. We do not even know which sub-basin they are talking about. We don't know the area. Is it the sub-basin? There's a full water basin of the river. We do not know anything about that, which is a real problem for us as hydrologists, because we understand the problem in its physics, in its domain. So the number of stations we were given were 1,500 almost. Each station is treated as a head catchment. We do know if a catchment is nested, but we do not know anything else. So this is kind of a future research for us. This is the distribution of the stations in the various countries. The United States is the one with most stations. UK is not represented here. This is actually a not so good graphic of when they start and when they end. This is 2015. Some of them, their ranges are actually vary. Okay. So this is really, this and the next slide are really dense. In order to, our goal, everything we did and we planned was to make a lot of runs so as to write a well-documented guidelines to assist the user. We did not manage to do that because we could not have the optimized models regarding hyperparameter optimization and lag time optimization. So our general conclusions are flawed. We cannot say that we can generalize, but we know that this is a good library for predictions as an initial step. So what we did as a workflow, an overall workflow, is to convert original NetCDF files that were given to us into Parquet files and CSV files. We actually used CSV. We have some bugs with Parquet. We analyzed the data sets and calculated the gap and streamflow metrics. We classified them based on missing rate of streamflow values and correlation of total precipitation observation and observed discharge. And we filtered out data sets following the literature. We're actually real optimistic. Some papers actually filtered out everything above 10% of missing data. So we filtered out, we removed missing rates above 50%. We removed, of course, ungapped time series. We removed number of gap days, 1, 2, or 3, because, okay, if you have 3 days missing in 20 years, you don't need us. And we had some problems with some metrics that need a lot of sample, a large sample. So we selected datasets with no gaps as our first step, and high precipitation versus discharge streamflow correlation, meaning that they probably are not dumped, they will have a natural flow, so we have higher probability to have good results. Literature says that also. And we introduced single at first, and of single gaps in various locations and of varying lengths, and then multiple synthetic gaps of various distribution and lengths and total number of gap days. These together were something like 7,000 variations of 13 ungapped time series. And we tested the performance there. There, the synthetic gaps were actually known, the true values, so our metrics, we can say that we're confident that these metrics apply. Then we tested 6 ML models, linear regression, actually the SDGR, k-nearest neighbors, support vector machine, random forest extreme gradient boosting, and light GBM. We used the recursive methodology. The direct methodology is actually, we call it that it is futuristic, but we have already done it, but we had not the time to present them. And we're calculating the metrics for performance in synthetic gaps, and then create results, which are the ones that I showed you, the plots together with tables with metrics, and of course the field time series. But then we redone all the testing with the filtered subset of real gapped datasets. And there, what we did is actually calculate the metrics in only the synthetic gaps and pray that the real gaps are filled in a nice way. So the actual challenge is to have synthetic gaps with characteristics representative of the real gaps. Then we created an easy-to-use Python library called HydroGap AI. It's actually on the repository. You can pip install it right now. And we wanted to draw conclusions on models' performance vs the classes of data sets. This is not the best thing, of course, at this point. We want to have the optimized versions of the models with the hyperparameter optimization and lag time optimization in their optimal way. So what the library alone does, it calculates the gap metrics, it identifies and indexes the various gaps in the real gaps in the streamflow time series. It creates synthetic gaps similar to the existing real ones to test the performance. So we do not have any split method. The synthetic gaps that we introduce are the ones where we actually calculate the metrics. We create features for training, which is lag times of streamflow, and we use a horizontal value of 3 here, so we only check the 3 previous values of streamflow and the 30 previous ones and for precipitation, because we have a large variety of rivers. Some have a lag of 2 days, the small ones, some have 2 months. Anyway, we thought 30 days is kind of representative. Of course, the user can change that, okay? The user can introduce his or her own values here. So we normalize data, then we use the 6 models. Of course, the user can select which one he or she wants to use each time. We predict the recursive methodology, and we calculate the performance metrics in the synthetic gaps. We know what the metrics are, and we create all these files that we told you, and we tried to write some guidelines which actually are the ones that I will tell you. So here we can see this is the initial gap metrics for some of the first filtered gapped data sets. And the gap metrics and streamflow metrics, no predictions yet. So you can see here that this is a really diverse set of time series. We have time series with 354 days missing, which is actually a lot of small gaps, and there are others with smaller gaps. So we have every possible distribution of lengths and number of gap days. And we have a lot of various differentiation of the Pearson correlation from the input stream precipitation and stream flow, which means some of them are really damped, human altered, some of them have natural flows. So we expected to have, and this was the case, in the natural flows, better results. So here we see results. We like to see the index of agreement, and this is in the single gaps only, we see it. We see that the index of agreement is better in the larger gaps. This is the gaps we introduced, one in many versions, gap only, in various locations of various length. We can see, and if we see the correlation coefficient in classes of, these are the gaps, the lengths, the versions of lengths of gaps we introduced in various locations, we can see that the index of agreement is larger in the larger gaps. So in linear regression, the same thing. We have an increasing value here. So why? Because we do not have hyper-optimization. You can see the difference without or with, and we do not have lag time optimization. We only had a horizontal way of introducing them, 3 for streamflow, 30 for precipitation. So you can see here, this is the small. We start from 3 days. We're going to 7. Here we have a negative correlation, but this is because we have a shift due to the not optimization of the lag time. So this is the problem. This is the explanation why in the large gaps we have better results, at least regarding the index of agreement. So this is what was only for the single gaps. We try to find in a correlation matrix if we have the same conclusion regarding the multi-synthetic gaps introduced and the real datasets that always have multiple gaps. This is not the case. We should find here in the metrics versus the characteristics some red spots, or at least blue ones, indicating correlation. This is not the case. This is, so around here we should see something. In real datasets, this is not the case. So we can say, because of this complex problem actually trying to being addressed as a black box, we do not have many of the crucial input features we need, temperature, the snow. So we can say that it's successful when we compare our results to the literature. It is a free Python for anyone to use and check. We think that all models produce reliable results, especially in rivers with natural flow or minimal human alterations. Tree-based models generally showed better predictive capabilities. We cannot prove it yet. XGBoost and LightGBM, of course, are the fastest ones of the tree-based. According to index of agreement, in larger gaps, it seems, at least in the non-optimized models, that we have better results. We cannot say it for sure, we cannot generalize, and we cannot give explicit guidelines because of what I told you, what the problems are. But it is work in progress, and we want to cooperate with the ECMWF for this. So future research, this is more dense than the conclusions. We want to explore and test additional machine learning models, XGBoost, MISForest, which does not need hyperparameter optimization. Incorporate deep learning models like LSTM and CNN into the library. In CNN, we can also take the gridded precipitation data, the land uses, and anything else that a hydrologist wants for him or her to predict from precipitation and all the input data, the stream flow. We want to include power generation data by upstream hydroelectric power plants because they are linearly dependent on water discharge, so it will definitely improve the predictions in human-altered flows. And we want to, of course, optimize lag times, hyperparameters, and develop a user-friendly GUI, GUI, to assist the user without programming knowledges, work on nested catchments, work on successive stations. We had 3 stations at one point that were in the same river. We can use this data. And use the direct method, it's actually done, instead of the recursive multi-regressor. Thank you for your time.
Excellent. Thank you very much, Yannis. Good. I saw a lot of numbers. Thanks for your for the insight into that. Are there any questions? Any hydrographers working with data?
Not a hydrographer, complete opposite. But on that theme, did you try some of the pre-trained models that are out there now, like Facebook's Prophet? It kind of would be a subject matter expert is not included, but it's trained on a lot of different time series, and it might be able to, just as a baseline, understand how that performs. Did you try that?
It should be some future research, of course. We had, we kind of addressed the problem as hydrologists that we talked about, that we cannot have a generalized model, just a standard one, but you're correct that it could be a pre-trained model. So the idea was that you cannot train a model in different rivers, which are really different, even their lag time is different. The water basin reacts differently in snow or rain or flash floods or anything. They're really different. So I think that as a hydrologist that a model could not be generalized, but I think that you're correct that we could have some small improvements, I think. If we have a pre-trained general model and a child which is only trained in our specific time series. Yeah, it's something that we will try. And if you want to help us, please do.
And then last question. Sorry, is there one on the line?
Yeah, it's Kostas online. So
he's Kostas Perifanos, our AI expert in our team.
I mean, there were various reasons for not going like that direction. We already have like a bunch of models that we want to actually test and see how well they perform. And I mean, from a practical perspective, my experience and what I've been hearing about, without having actually tested on that data set, that's definitely something that needs to be done. Prophet or deep prophet. I'm kind of like get mixed feelings from people that are using. Some people hate it, some people really, really love it. But generally, it's most probably an extremely good idea to give it a shot at some point.
Yeah, I think time series forecasting is super hard, so it's not an easy project. Last question from me.
Short one.
Okay, sorry. On these gap length, essentially from your synthetic gaps when you try to train the model on that.
Sorry?
Do you know the synthetic gaps you introduced to try and train the model?
Yeah.
Did you try, because you said you tried using the same types of gaps you found in the data, did you try varying it to see if that kind of helped increase the amount of data you use to train? Yeah, so vary the gaps, so you'd have more data.
We do have, the multiple gaps are actually of varying lengths, So we actually wrote a code that introduces, that has to have at least one day gap as a minimum length gap. It should have one gap with a max length of the real gaps and kind of have a normal distribution in between. That's it. So this is why we actually had 50% above missing data filtered. We should have more because if we, at some points, the data for training were really low. So yeah, we did it. Yeah, this is. But I think the improvement should be there. We should try different. We can't prove that the metrics are correct. So this is a problem. We want to find a way to actually have confidence that the synthetic gaps are representative of the real ones. This was our way that I told you. I hope it is representative.
Okay, thank you very much, Yannis. Another round of applause. And Thank you. Our next speaker or the next project, the one before lunch break. So everyone active still? Yay! Yeah. You did the learning curve from this morning a little. That's good. Okay, we have here Mario Santa Cruz, who is the mentor for the next project, which is XAI for weather forecasting models, and we will have Mihaela, Andre, and Adrian participating online. And the goal of the project is to develop explainability techniques and approaches of transformer embeddings for weather forecast. And Mario, you're the mentor. First,
Hi, hello everyone. So I'm part of the AIFS team, and me with other colleagues from the Bonn office proposed this challenge to address some of the concerns of the AI models, like understand what are they doing under the hood. So Mihaela and Andrei have been working for the past few months on this topic, specifically for tropical cyclones. So I leave the floor to them, and I expect that you get some interesting insights.
Okay, can you hear me?
Yes.
Hello?
Yes.
Can you hear me?
Yes. Yeah.
So can you hear me?
Yes. Can hear you. We can hear
You
you.
can hear me?
Yes, we can
Hello?
hear you.
Oh, okay, sorry. So I can start my presentation. I will share the screen.
Yes.
And please let me know if it is all okay.
Yeah, we can see your screen. It's a PDF. Don't know if you want to go into presenters mode.
Yes, I will scroll down this. Yes. Can I start? Yes?
Yes, please.
Our topic is investigating explainable feature in weather forecasting AI models. And for this, we use the AIFS model from ECMWF. And the target of our investigation was, as Mario said before, storm tracks and extreme storm tracks in the northern hemisphere, mainly. This is the reason for this is, of course, what we see in present and all the statistics. Here in right-hand side, you see the accelerated increase in annual economic losses, and not only caused by these climate extremes. And also here I put a passage from paragraph from IPCC stating clearly that frequency and intensity are projected to increase in Europe, Northern, Western, and Central Europe. The approach that we used for this work was basically starting from the idea that we need to investigate if physically meaningful initial perturbations or variations in the conditions are further resolved in the model, such as to lead in a consistent, physically explainable response produced by the model. So if the model is able to use the learned teleconnection during the training phase, and not only to learn, but to use them along the forecast, or if it's producing the forecast and the mechanism of extreme amplifications respecting physical laws. So for this is a scheme of the work package that we developed along this project. We have 4 work packages, and the output of each work package is uploaded on the GitHub. And I will tell very quickly which is the output of each work package, that any user, potential user, or someone interested can make use of it. The first work package here, we developed a code, a software code, that allows a user to specify predefined, physically coherent, physically meaningful initial conditions perturbed in the main drivers that are characteristic drivers for storm tracks and for weather in Northern Europe in general. So the output of this work package is a package called Fortran, Python and Fortran. We put both software, we develop both software in order to be broader, for broader use by any user. The other package is when performing simulations. So we're using the initial conditions introduced and by this code, we perform then the simulations, the AIFS simulations, and the output is a full databases of extreme events during the spring-winter season of this year. Anyone can take the results and analyze and further make use on it. The third package is a package that we developed in order to analyze the results that we got during the simulations. This software is a full package developed and available also in GitHub and contains more submodules that I will describe further on. The aim is to really analyze if the outcome along the forecast is physically meaningful and to retrieve explainable features from the AIFS model. The fourth package is how we analyze the results from VP1, VP2, VP3 in order to trace features, explain features, emphasize them, and show that if and how they are used by AI models in producing forecasts and in the mechanisms of producing mainly extreme situations. So the outcome is preliminary results. Just very briefly, I will introduce the VP1, the package of computing perturbations in the initial conditions. These are two types of perturbations that we thought of. They all target the main drivers of the storm tracks and of the weather over Northern Hemisphere in Europe, and Europe mainly. And these are features, drivers targeting the fast flow, impact on the response and the slow flow on the response. Of course, this layering is useful for interpreting the results and layering the results upon the two model AIFS and IFS. And interpreting the relative skill of each one model versus the other. So the type of the perturbations are two types, global and regional, and all are targeting the main drivers of the storm tracks. The global perturbations are mainly the jet, which is the main driver of tracks, with perturbations in meridional zonal component and cross perturbation, and the phase of main modes of variability and of coupled modes. And the regional drivers for these events that are also coded, all are coded and are found in the packages, software packages in VP1. So for regional perturbations, there are coded 7 perturbations in the sea ice, SST anomaly, North Atlantic, Central Atlantic, and so on, SST tripole along the America coast. El Nino 3.4 is coded in the package, and two types of NAO perturbation, the gradient and the phase adjustment. Just to show how one can know more about how to use the VP1, the documentation in VP1 shows each function, how it can be used by the user, how the options can be specified, like the location. Here you have illustrated the location of including a warmer area in the Central Atlantic, and here what the result in the initial conditions after inserting this warmer area. The same for the SST tripole, sea ice, and so on. So these boxes are repeated and found in the documentation and present how a user can put different his options, and perform with these simulation. Further on, Andrei will show a practical use of VP1, because this can be of interest for anyone interested to go deeper into this aspect. I will let Andrei.
Okay, so I'll share my screen. Okay. Okay, so I'm going to. Sorry.
Las pe mute, vă rog frumos. Las pe mute.
I'll show you. So I'll show the demonstration of what we how we will use what we've prepared. So first, we need to have some initial conditions, the ones that we are going to perturb. So mainly we'll have the jet parameters that we are going to perturb. And this is what sorry for the okay, sorry for the disturbance. So we are going to perturb the initial conditions. So first activate the Conda environment, then run the Python CLI, which perturbs the initial conditions. Okay, this we're done. Then we're going to run the AFS prediction for 10 days, which now we shall see the GPU loading the memory here in the NVIDIA toolkit. This takes not that much, maybe less than a minute to run. Then we're going to visualize the results using this notebook, which is provided also in the GitLab, in the GitHub repository. Okay, so now everything was done, and all the results should be here in the GRIB files. The GRIB files, experiment GRIB files, and here we have several experiments. Right now we're going to focus on the storm that Mihaela was telling you about earlier, and then I'm going to run the search from the notebook. Here we have a widget where we can select the initial conditions. So we are going to select 2nd of March. Then the next widget, we are able to select the perturbation file. So we're going to select the Carlota storm track. Then we are going to view the initial conditions. So in this toolkit, we have 3 figures. The one, if we would have a polygon, we should see the polygon on the map. But since everything is global, we have none showed here. And then we have the initial conditions in 2 time frames. That's what AIFS requires. So the 0 at 18 and at 0 UTC. And now we're going to run the visualization for the predictions. So yeah, let's wait because this is the old one. And we will be able to navigate through the predictions with this slider tool. So in the initial conditions are pretty similar, and as we go further, we shall see that differences start to appear in the predictions, and we have different outcomes. And here we have 40 time steps, so 10 days and 4 hours for each day. And that's about it. What we can use this toolkit. We also have developed some Pangu predictions and other helper functions, but this is the main visualization tool. And now I'll let Mihaela show you further the explanations for the prediction.
Okay, can you see me? Can you hear me? Yes. So what Andrei showed, I just want to comment that indeed the perturbation that he used the perturbation, he selected the perturbation in, Andrei selected the perturbation in jet at 300 hectopascal, and he selected the meridional velocity enhancement. And I want just to point out that the model is responding exactly as expected from this physical meaningful initial change. So just changing the initial conditions, the model allows now enhancing the meridional velocity, so it is allowing enhanced amplitude of the waves that are driving this tract. And in the storm example of Charlotta, where three steps that were important, the one step affecting Italy and France, the second switching to Adriatic, and the third in Greece, and indeed allowing this enhanced meridionalicity or wave amplitude, the model was able to push farther south the cyclone, as in observations, as I will show immediately, in the first step. And in the last step, he was able to capture and to keep around the perturbation on the southern area over the Greece, and not to go towards upper latitudes as in the control simulation. Now I will go further on to describe very quickly the VP2. So in the VP2 there is a whole databases of all these simulations that we performed, and also all the initial conditions perturbed, non-perturbed. So someone can directly analyze further on the other of the 7 perturbations that we initially put on the slide as regional and all the global one. In the VP3 I will show the diagnostics package. This is a package that we developed fully with a few sub-modules in order to allow us the analysis of the way the model, the AI model, is able to produce the forecast and to enhance the development in extreme cases. So one module is identification of cyclone, the other linking tracks, the other identification of extreme situations, and maybe the main important one is the diagnostics package, which are varying from central pressure differences if you use more models you want to compare. But the main important one for analyzing explainability are also this one. So various energy computation and energy conversion that allows us to go deeper into explainable feature and understand if the mechanism of a model amplifying the extremes is the same as in the deterministic model. The persistence is also a very nice feature which allows us to say how many time steps a storm remains in a same subdomain as a local minima, in order to have a clue if we will have accumulated precipitation in extreme or not. So these are important features that are all coded in the package and available on the GitHub. The presentation is like this. I will make yes.
Sorry, 5 more minutes.
5 more minutes.
Okay.
Thank you very much. I will be very quick. This is another demo for the third work package for the diagnostics, just to show that it works properly. And here I stopped the simulation in the first phase when to show just that the response to the jet is a physically meaningful one. So this is one of the main explainable features of the model, because the deepening was pushed farther south. I will go back now here, and I will show, so this first one example of the explainable feature found was the main driver of the storm tracks, and so the jet. And we see that when we enhance the meridionality, we get a more cyclonic area, while when we decrease this, the tracks are deepening, are filling in. And a second that I will take only 1 minute is explainable feature identified is one of the most important one, is the phase, the accuracy of the phase in the initial time. And for this there is a full package that allows us to correct the initial phase over the 2 time steps of AIFS by using previous 10 days of observations and computing from this the tendency of the PC coefficients that correct the phase and in the initial time. And these are the results of corrections that are very nice. They show that if the signal of the correction is a negative NAO, they will lead to a stronger deepening of the cyclones in the key moments of the evolution. Now I will have only 2 slides, what we do in future and the summary. In future, there are the other features that are already coded and simulated on the databases that can be analyzed, like CI's predictor, other property of the phase, or the type of the error growth versus IFS that can bring important information on the extended predictability beyond 4 days. And now the last slide is the summary. We wanted to investigate the current understanding of AI explainable feature. And really we developed a full package of 4 sub-packages that allows us a tool to investigate this. And we also put in emphasized that indeed AI model, at least the AIFS that we investigated, presents explainable features in the main drivers of the storm trials, like the jet, and also like the phase of the main modes of variability. This information can be used also for explaining the skill of prediction, but also for improving it further on by exploiting this information. Our future interest is to further complete this, or someone else, any user can use the code and the databases to further analyze the other feature of explainability. And finally, to answer the question, is the model, so we really partly show that we are encouraged that the model AI is using learned teleconnection not only to learn, but also in forecast, along the forecast it is using the learned teleconnection to produce skill. And in the extremes, to understand the mechanism, the physical mechanism of extremes, we have the work package that is really fully exploitable. In the end, we want to see, to emphasize with these explainable features the limits and the powers of each of the 2 solutions, AI models and deterministic models. And we think that this package can be further on exploited to push on the knowledge, the actual knowledge on that, or at least to bring more information on this. And the last and very important slide is that we thank you all for the support and for the collaboration and for the whole team for us.
Thank you very much.
Stop sharing.
Yeah, thank you very much. Round of applause. Yeah, thanks, Mihaela and Andrei. I'm looking at the audience here. Are there any questions? No, we are all tired and hungry just before the lunch break. Checking online. No, I don't see any questions online. So a big thank you to Bucharest. Another round of applause. Thanks, Mihaela. So welcome, and I think we are also online. Welcome to the afternoon session. I hope you had a good lunch break, enjoyed some sun. It's amazingly beautiful here in Reading. Sun is shining. And now we enter into the afternoon session. And we have 4 presentations, and I would like to introduce the first one. That's the MLBs. And the goal of the project is to improve the performance of ECMWF's current land surface machine learning model prototype. And we have Yikui Zhang, Till Foreman, Johannes Leonard, Mohammed Hakam Shams, Adrian, and we have the mentor of the team, Yuan, who will give a few introducing words. Thank you.
Cheers. Yeah, so this project was really about trying to emulate the Earth's surface. We'd done a bit of this at ECMWF already, but we had sort of lots of questions about how this could work better or be more efficient. And so the team has been really, really good throughout the project. It's quite diverse, and I think they've all really been complementary skills to the project. And yeah, it's gone very well, and I think we've learned a lot from it. So it's been a very nice project. So thanks a lot, guys, for all your efforts, and I'll pass over to you now.
Thank you for the kind introduction. We do share that sentiment as well. And yeah, so we are MLBs because, of course, we had to choose a silly acronym, and it's short for Machine Learning-Based Emulation of Land Surface Models. In this case, that's EasyLand. So why you might be interested in these talks could be the following reasons. So, I mean, we already heard that machine learning is all the rage now. You trade off a bit of accuracy, but what you get is a lot of speed up, so that makes it interesting for a bunch of applications. And in this case, it is no different. My personal highlight, though, is that we tried a variety of architectures. Sometimes that's not all too exciting because you should see then a model comparison where you see some small changes in some model metrics, which can be quite abstract. But what we really saw were some appreciable differences in qualitative differences in the model outputs, which you can then also try and explain either by physical reasoning or by the model architecture itself. And since we tried a bunch of architectures, we had to come up with a simple automated evaluation script. This should be easy to add on to later if that's desired. But we also wanted to make sure to do an in-depth evaluation, because with these statistical models, there's always an issue with how reliable are these outputs really, and that's why we tried to scrutinize them. And then we'll start on a visual highlight. So Johannes prepared this nice animation. On the left you can see EasyLand, so that's the original. On the right you can see one of the emulators, and this is layer 1 soil temperature for a year. Just for you to see how similar or different it looks, and what kind of data we're talking about. Before we get into the details, though, I want to take a little step back because maybe not everyone's familiar with land surface models. So what they do is they solve the energy, water, and carbon fluxes at the land surface, and then you use those to predict future time steps, so soil moisture, soil temperature in this case. You could either use the standalone for flood or drought forecasting, or you could use this, mostly use this in a coupled fashion with a weather prediction model, because of course the exchange between land and atmosphere is quite important for getting the weather right. And here on the right you can see a schematic of EasyLand. So this is not for you to read through, of course, but just to appreciate that there's a lot of processes going on. And so it takes a bit of computational effort to actually solve all these equations that come into play here. And what Ewan, who just introduced us, nicely demonstrated with this prototype already is how much of a speed up you can get. So if you run this full model for a month at a global 30-kilometer resolution, this will take you like 20 minutes approximately. And if you go to machine learning, then you can really go down to a matter of seconds. So that's quite impressive, I think. So what we did in our projects were mainly two pillars. So on one side, we have the model development part. There we wanted to improve on AR-Land by unifying the data processing pipeline, testing different methods, as I already said, incorporate some observations, and then also we wanted to try and constrain the emulator to be physically consistent in the outputs where possible. And this goes hand in hand then with the evaluation part. So we had to look at accuracy and at the speed of these different versions. And then in the in-depth evaluation, we looked at spatial and temporal error variability. So what we mean by this is we had the feeling before we started that maybe there might be some regions of the Earth which perform better or worse. Maybe there are differences between seasons as well, and this is what we wanted to find out. Then when we incorporate observations, we also want to compare to observations as well, test the physical consistency, and have a look at uncertainty as well. And now Johannes will start by talking a bit more about the model development part.
Yes, thanks to. Next up, I will give a bit of an overview about which kind of methodologies we actually used to emulate this EasyLand model, and also just how it all works. So starting out with more or less the inputs to the model, we have, of course, most importantly, some model states, which here, symbolically, you can imagine just one model state at some time point. So this contains information about like soil moisture, temperature at various layers within the soil, and also the snow cover. And then, of course, we also have some auxiliary information, and this can be static conditions, like information on the topology or the land cover. but it can also be dynamic. So this includes the weather or vegetation-related variables like the leaf area index. And then what we also add is additional inputs. Is spatial and temporal encodings, and these basically inform the model about where on Earth a certain data point is located, and also about the time within the year, or also the time within the day that we actually try to emulate. So all of this is fed into AI Land, which for the time being, could be any machine learning model actually. And this machine learning model is then trained to predict, on the one hand, some state increments. So basically how soil moisture, soil temperature, and so on progress from one time step to the next. And it also predicts some diagnostic variables, which are basically variables which are not directly incorporated in the model state, but are still interesting in terms of land surface modeling. And then, of course, we can use this emulator as we do the regular model iteratively. So we can use the predicted state increments to update the state and just rerun the model. Okay, so next I will talk a bit about data preparation, which I know is for a machine learning audience always a more or not so interesting part, but it actually was pretty crucial for us to take good care of this. So first of all, we have like the ECLand output for a grid over Europe. So this is a model run which is at a 6-hour interval from 2010 to 2022, which we divide into like training, validation, and test set. And then we have to take some care about the standards, data standardization, because of course all these variables which I mentioned don't share units, so we standardize them by mean and standard deviation. And also for the increments, we found it important to standardize not on the original variables, mean and standard deviations, but actually those of the first differences to actually get a stable model run going. Okay, so this data is now trained to used to train a machine learning model, and here we actually compare 4 different ones, which you can see on the left. So first up we have XGBoost, which is basically an ensemble, a boosting ensemble of decision trees, regression decision trees. We train up to 1,000 of these until up to which it's still sort of reasonable to go up in size. And these decision trees, they basically use a gradient boosting mechanism to iteratively minimize this some predefined loss, in our case the mean squared error loss. Then we also train a multi-layer perceptron, which is a very simple neural network. We use dropout and also train it on the mean squared error loss. So both of these models, the XGBoost model and the MLP, they basically run grid cell wise, so they can only predict the predictive variables at a certain time step at a certain location. And to improve upon the situation, or to also look at other possibilities, we have the other 2 neural network architectures. The first is a graph neural network. So graph neural networks, as their name suggests, operate on graphs rather than individual data entities. So this basically enables us to also incorporate some spatial information into the network architecture. So throughout the network architecture, neighboring grid cells are able to communicate, and we were hoping that this would basically improve the network capabilities. And then secondly, we also want to take into account temporal information by using this Mamba architecture, which basically operates on sequences. So instead of just taking a previous time point, we can actually train the model on sequences of up until, I think, 64 data points rather than just the previous one. And also note, so this relies on, this model basically relies on selective state spaces, which is a bit more efficient than the transformer architectures that you may know. Okay, so now for the actual evaluation of all these models and the comparison, I will hand over to Yikui.
Yeah. So thanks for Johannes for introducing the methodology and machine learning model. So to evaluate our machine learning emulators, so we first streamlined the automatic evaluation framework or workflow to calculate the evaluation error matrix from using data from both the ECLand model and also the validation data set to evaluate our AI-land model, our machine learning emulators. And at the same time, this automatic workflow is also used to visualize the spatial error map of the evaluation result, and also finally to automatically generate a scoreboard to summarizing all the results. And based on this evaluation matrix, so we further did statistical attributes, conditional analysis, and also uncertainty analysis, as well as the physical consistency analysis. So first of all, we summarized the result of our 4 AI-land model or machine learning emulators in the result for all the target variables, or 16 target variables into this scoreboard. So here we only show the example of the anomaly correlation coefficient as the evaluation matrix. So basically this matrix, it means if this, you can easily understand it's close to 1, the better the model performance. So here we can easily see that actually the XGBoost model performs best for most of the variables. And it's very interesting to see that the XGBoost model outperforms most of the neural networks. And among the 3 types of neural networks, we can see that the Unimap model, the graph neural network model outperforms other types of neural networks. And despite of the difference between the model performance among these 4 types of machine learning emulators, actually all of them can achieve a very good performance for most of the variables. And the only exception is for the discharge and also the surface runoff. And we can see that here for all these machine learning emulators, the anomaly correlation coefficient is lower than 0.5, which we can say that there is a very low emulation performance for all these 4 models. And on the other side, so considering the trade-off between both the accuracy and the efficiency of the machine learning emulators, we can say that the MLP model actually is the most efficient model we have, because it can achieve for its inference, it can achieve 44 time step per second in the inference, and this is around 7 times or 6 times faster than the XGBoost model. But of course, this is somehow sacrificed its emulation performance. Next, we visualized. We want to show the spatial error variability of the machine learning emulator. So first, here we show the example of the anomaly correlation coefficient of the layer 1 soil moisture for the 4 types of machine learning emulators. From these 4 figures, we can easily observe that actually our machine learning emulators can achieve a really good performance in most of the regions in Europe in our target domain. We can see that in most of the grid points, the ACC score actually is very close to 1, which means that the emulation performance is quite good. And however, there's also one interesting pattern is that all the machine learning emulators somehow struggle in the Scandinavian regions. And especially for the MLP model, is this low performance somehow extended to the east part of Russia. And this is likely attributed to 2 reasons. So first is the difficulties for the machine learning models in emulating the snow melting processes in these cold regions. And the second reason could be related to the difficulties of the machine learning emulators in dealing with some special land cover type, for example, like lake or glaciers. And next, we also did some analysis to test the physical consistency of our machine learning emulator. So here we show an example of the sensitivity of the soil moisture to the field capacity. So in this figure, we show the sensitivity of the soil moisture to field capacity calculated by the MLP model, and we can show, and these points basically represents the relationship at different selected locations in Europe. So here the MLP model shows the gradual reaction to the change the field capacities. However, sorry, we didn't show the figure here, but the same figure for the XGBoost model, it shows that average soil moisture jumps at the learned field capacity threshold, and this is corresponding to the different soil types. So this is somehow related to that tree-based model. It prefers or it tends to learn a discrete relationship rather than a gradual change. So last but not least, we also try to evaluate the uncertainty associated with our machine learning model. So in this project, we only focus on the epistematic uncertainty, and in order to capture this uncertainty, we adopt a method called deep ensemble by simply creating an ensemble with 30 UniMap model members with exactly the same neural network structure, but slightly different initial condition, or basically the slightly varied parameter size for these 30 neural networks. So in order to quantify the uncertainty, we calculate the continuous ranked probability score for the at both spatial and temporal scale. And this, you can easily understand this metric is close to 0, the better the performance, or the lower the error of this ensemble. So from this figure, we can show the spatial variability of the CRPS score, and we can actually see that it shows a very similar pattern to what we have observed in the previous spatial error variability analysis. And we can see most of the places there is a very low score, which means that the uncertainty associated with the ensemble is quite small, but there is a relatively higher score in the Nordic region, in Scandinavia regions. And actually, this further demonstrates that our deep ensemble method can somehow provide a very reasonable estimation of the uncertainty, because the well-calibrated machine learning model should provide small uncertainty in regions where we have a small model error, and high uncertainty in regions where we have high model error. And finally, I will hand over back to Theo for the conclusion.
Yeah, thanks. Yeah, there would have been a lot more to talk about, but there's no reason to be sad because everything's on GitHub as well as the documentation. So just a few take-home messages. So we saw that XGBoost is already sufficient for emulating ECLand, which was quite a bit of a surprise to us. There are a few drawbacks, so it's a bit slower and it's a bit less flexible than other models. And also we didn't really show that here because of time, but we saw how including these spatial relationships really helped in mitigating some of the artifacts. So if you predict every grid cell by itself, of course, it can then lead to some discontinuities in the spatial domain. We saw how, exemplified by Scandinavia here in this one map, the emulators all struggle a bit with cold regions, especially glaciers, and also waterlogging areas, so close to lakes, marshes, also are a bit of a problem. The good news in terms of the temporal error variability, so it's boring, that's why we didn't show it, is that the seasonal and the diurnal cycle work quite well, so there's not much difference in performance between autumn and winter, for example, or between day and night. And so finally, I would like to use this opportunity to thank all of our mentors. We had really great discussions and learned a lot, so we really enjoyed that. And so, if you have any questions, feel free to ask them. Thank you for listening.
Yeah, great, thank you. Are there any questions? Yeah, there's, yeah. First, Matt.
Hello, thank you very much. You're emulating a data set that is local, is that correct, from ECLand? So how do you attribute the success of a non-local machine learning solution over the local machine learning solution, i.e. comparing the MLP with the graph solution? Why do you think it should be better if the process you're trying to emulate, the grid points could be shuffled up, the interrelationship between them should make no sense?
Yes, so indeed the model itself already runs grid cell-wise. What we noticed is that there were certain very specific points where the model somehow gave us not really physical results, especially in these regions that were discussed. So we thought one way to sort of mitigate this is to also incorporate information from the neighboring grid points. Just to maybe have the model then use this information rather than the one at the grid point, which may not work. Specifically in snowy regions, this was a problem.
But the XGBoost is able to handle these weird points in the data.
Yes, so the XGBoost, since it operates like on a grid cell level, so it operates on each grid cell individually, it more or less just has no chance of, since it just starts out also with the data in these grid points, which we found to not work in a physically meaningful manner, to update the state accordingly. Whereas when we also incorporate the neighboring grid points, we sort of found that it got more useful results in parts. This was very isolated and doesn't really not really reflected also in the metrics that we provide maybe, but it's something we qualitatively maybe found.
Great. Thank you very much.
Do you have any idea how would you go about improving the performance in the areas where it's not performing well? So Scandinavia, the Alps. It's not all glaciers, I think. The area where the performance is bad is certainly not just where the glaciers are, but it's beyond that. So how would you go about improving it there?
That's an excellent question. So, I mean, one of the things is that we tried is incorporating the observations into the training, but as far as I remember, that didn't work out so well. So this might be a cure, but it's not there yet. Other than that, I don't know. I'm not the machine learning. I'm not a machine learning expert, but maybe it would also help to kind of separate the problems a bit. So, for example, these lakey areas, they would deteriorate quite quickly, but maybe if you have a model that really looks into lakes and not mixes different processes, maybe that could also help.
Yeah, I think as Theo mentioned, like so we have in this region we have problem probably in learning some special processes like the snow melting processes, and it might be possible to integrate in this kind of physics in the machine learning model, for example, as part of the loss function. But due to the time limitation, we didn't try this. But this might be a solution, for example.
Okay. Are there any other questions? Sorry. I'm checking if there's online questions, but no online questions. So another round of applause for the team. Thank you very much. And we are moving on to the next. Miha was one of the mentors. We reached CAMS NB charts, and that will be an online presentation by Akis Karayanis. And the project is about to help users plot CAMS forecast charts based on their needs via Jupyter Notebooks. And you do a short intro.
I can do it.
Yeah, thank you.
So you've heard already about the Copernicus Atmosphere Monitoring Service, what we do. You heard a little bit about Atmosphere Data Store. So this is where we publish all our data sets. What we also do is that we publish a lot of graphical products. So we have a website where we publish daily forecasts. We publish plots from the reanalysis and from other data sets. And what we get asked a lot is that, how the users can replicate this. And, the way how we do it at the moment is not really well organized and sane, but so we want it to improve. So it's kind of born out of laziness. So what we would like to achieve is to have this kind of offer this kind of reproducibility, so that it's very easy for anyone, for internal users, for training courses, for media organizations, whoever wants to replicate anything, that is able to do it, but also then to have a kind of framework to update this, and when new products are added, just add new methods to replicate. So I give floor to Akis.
Yeah, Akis, your turn.
Hi, can you all hear me?
Yes, loud and clear, and we see you.
Yeah.
Yeah.
Good. So I'm Akis. I worked on this project. The main goal, as Miha explained, was to write some code to reproduce CAMS forecast charts programmatically. So use Python to generate these charts. So the aims of the project were to streamline this process, which, as Miha said, was kind of disorganized. So different people within the ECMWF, or maybe outside of that as well, had different code bases, different routines, different plotting styles of doing that. So one of the aims was to streamline this process of accessing data through the ADS and plotting the charts. For plotting, to use or maybe reuse the EarthKit Python package, and more specifically the EarthKit Maps module, and give some functionality of different users to be able to use this tool within a Jupyter Notebook environment to both generate Jupyter Notebooks for training purposes, for example, or generate these charts within a Jupyter Notebook. Now, one of the challenges was bringing different bits and pieces under one roof. So, as I said, different people had different pieces of code or different styles for plotting, like different color scales. So, one of the efforts initially was to collect all of these. So the mentors gave me some code and gave me different styles and color scales to put them together in a structured way, so we could have a single repository, access that, and generate those charts. Now, for example, some of the styles of the plotting styles look like this, or at least they look like this now. So you have the name of the style. This is for aerosol optical depth, for representing that variable. You have a list of colors. These are looking nice. They're from normalized RGB values from 0 to 1. Some of them were 8-bit indicates from 0 to 255, and some others were like this, using an older tool, the Magix plotting software, where the colors were in names, and some were found in the documentation, the mappings to those normalized RGB values. So we collected all these together, put them in a configuration file. As you'll see, the project is based on several config files, YAML files, where we handle these mappings, and we put it in a structured way, so you can grab the style that you want to use and visualize the plot in a different way. Currently, there are 8 CAMS variables supported. It means that there are entries in the several configuration files for these variables. And there is a different YAML file, configuration file to handle that. So here you have aerosol optical depth. And in its entry, there are 3 sections related to that. One is data request, which handles data access through the ADS. So the parameters here are used to build the actual data request. To fetch the data, this is the data set that the variable comes from, the type, and the actual name of the variable. You have plot attributes, which handle how to visualize the chart. Now, the title, for example, and also a default style. So if the user doesn't provide any custom style or another relevant style for that variable, then the code defaults to a pre-configured style. And also you have a post-processing section where you handle conversion in different unit of measurements or scaling the values. Now this is under forecast.yaml, and having these config files, it's very easy to extend. So if you want to extend to add one more variable, you just follow this template and add one more and one more. So hopefully over time, this will be, this tool will be used to produce many or all CAMS variables. Now, the third and final config file is the one, those two were the default ones, right, pre-configured. Now, for the user to generate a CAMS chart, they have to fill in some values in a config.yaml file. And this is really, the value you want to fetch, the date and time that you will use as a base time, and how many hours ahead is the focus that you're trying to fetch. And also, override some attributes. So in reality, what happens is that you get all of these config files together, and you give priority to the one that the user entered. So if they use a custom style, that gets priority over the default ones, and that goes for all the attributes, the parameters that the user puts in their config. And yeah, this is a CAMS chart for Azure Optical Depth generated. The one on the left is the one that was at the time available on the CAMS platform, and the one on the right is the one that was generated using, programmatically generated. Well, they look quite the same. There is an issue counter that we'll explore maybe later. That's where the color bar stretches, but that's for figuring out later maybe. Let me just demo this functionality at least. Just can you see my screen? Can you see the other window?
Yes.
Brilliant. All right. So the code is up there. I'm not sure it's public yet, but you just download it, create the virtual environment for Python to run and install the dependencies, and there are already those config files available. So for example, this is the forecast config file where you have all these different CAMS variables, and as I showed previously, you have different conversion factor and units of measurement, all of these parameters for accessing data and plotting it. So for example, for the, where is it? For the aerosol, the default style is this one, and then you go to the styles file and you see all these, the color list and the different levels that make sense for that variable. You see it here. And the final one is this one, which is the config file that the user has to fill in to access the data. There's a credentials section here as well, where you have the API key from the ADS. So, for example, if we want to fetch particular matter, let's say today, 24 hours ahead. Yeah, then you fill this. I try not to reveal my API key. And you just pass. Oh, one more, you have the where to store the output, and this is this folder, chart.png, which is this one. And here you can see, particular matter for the forecasted day ahead, right? Let me go back. Another aspect of this project was to have the functionality to generate a notebook, but programmatically. So run a script and output a Jupyter notebook. And again, to do this, we used YAML files, right? We used templates, which they have some conventions, right? So such a template is the one on the right, where you have you generate the template relevant to the aerosol optical depth. Here you can see the markdown cells, and also there is a chart cell where you actually have the output chart. And this sample template could be used for training or could be used for communication, because in this sample you explain what the variable is and how to interpret what you see in the chart. Again, it's very easy to add, if you follow the convention, it's very easy to add another template for a different purpose. So you'll see in the config file that there is one more section which is related to notebook. Right now, the chart only is true, so you only see the chart. Ideally, at some point, we are going to have another option to also reveal the code that runs to do this, maybe to have this end-to-end and have all this information from the template and also have the code and the output chart. And then again, you have the output path where the Jupyter Notebook is going to be stored. And this is the notebook you get at the end. Let's do that as well. So for example, if I go here, go to the config and again, today, 24 hours, and then just run this, which will hopefully output here a Jupyter Notebook. That is the data, right? So sorry for exiting here, but not this one. If I go to output, notebooks, IRD. So this chart.png is the one that was generated for this purpose, and it's here, so the notebook knows where to fetch it from. And this is the Jupyter Notebook that was rendered through that script. So again, for training purposes or anything the user wants to do, as long as they add another template, some information about the variable, the chart, and how to interpret what you see. And the last one, which was nice to have, because we put all these to-dos in the beginning and all the ambitious targets, but when we tried to wrap up, we saw that some things were left out. So when I tried to put this in a Jupyter Notebook, I said, let's try to produce not just a chart, but also an animation which is available on the platform when you go and see it. So even though this is not in the in the actual scripts and the core utils within the Jupyter Notebook that I have added in the repo, you can generate these GIFs. Let me go. Where is it? Here. Actually, not here. Sorry. Let me go here to the config and just. It changes the lead time hour to give 6-hour intervals, starting from today up to 78 hours ahead, right? And once I do this, I go here and let me just run off cells. So this notebook, if someone goes to the repo and access that notebook, says what to do before you run it. So you fill in the config file, explains what its parameter is, and really what it does is gets bits and pieces from the core scripts into this, like the utility functions that fetches and merges all these configurations in the parameters, initializing the CDS API client and retrieving the data. Oh, here it's already downloaded. and how to process data and plot it. So this is built. The animation is done through Matplotlib. So what we're doing here is just store its chart and then put everything together into an animation, which is great if you want to have a dynamic view of a variable. So, for example, here you can see, aerosol. This is probably from the fires in Brazil, right? So you can see how it extends over time. Nope. So hopefully this project will be valuable to both people in the ECMWF and external users, and streamline the workflow from data access to visualizing those charts, and offers a structured way of doing that. Now, from the very beginning, it was a requirement to use configuration files, and this proved to be greatly beneficial, because not only you can configure how several parameters, projections, or plotting styles, but also you can extend the capabilities of the tool by adding more variables or more node templates, or more custom plotting styles. And again, by adding more templates, which is fairly straightforward to add, you can programmatically generate these notebooks, and even though it's not in the core scripts, you can have some kind of animation you can generate it, which will probably, as I say here in future steps, will implement it in the core script, so people can actually generate an MP4 GIF file. So for the future, because I'll try to keep track and add more things here, even though the code for Earth ends today. The plan is to add a few more variables, and one thing that is not present is the main options. So you'll see when you go to the CAMStats platform that you can select based on continent or country, and you get the zoomed in charts, and support for more projection, because right now there is the option in the config file, but if you select anything else, it's not really there, so the mapping doesn't exist right now. And finally, to resolve that max level issue, that you cannot really see the difference between the charts published on the CAMS platform, apart from the maximum value of the color scale right on the bottom. So probably we'll publish this code to make the repo public, which is here. Yeah, thank you very much.
Thank you very much, Aki. Good. Are there any questions for Akis? Do you have him online? Any questions? Everything clear? Yeah, Akis, it seems there are no questions for you right now, but there's he put up the GitHub repository, so you can also look at that and get in touch with him. Thank you very much, Akis. Greetings from Reading.
Thank you very much.
Yeah, so we are now moving to the next presentation, which is entirely online. We have Luke Jones, one of the mentors, who will introduce his teams, the CAMS visualizer. And the project is about to visualize CAMS verification data in a flexible and easy way. And the team is from Turkey. We have Hakan Deniskel, Yavuz Arda Orak, and Elif Rana Arslan. So Luke, first you, and then Hakan.
Okay, so hi, can you hear me? Okay, please. Okay, well, let's assume you can. My name's Luke Jones, and I work as part of the CAM project, in which we make daily forecasts of and historic reanalyses of atmospheric composition, such as pollution, dust, and greenhouse gases. And as part of that, we need to be able to verify our model outputs. And we have our own software to do that, but the main piece of software was only designed to output static image files, which are then navigated by a browser application which just displays them. And that means a run of the code spends a long time generating hundreds and hundreds of images, most of which never get looked at. And if the user wants to see a plot which hasn't been produced, they have to run the whole thing all over again. So what we wanted was to be able to output just the raw forecast and observation pairs and have the plots made dynamically in a more advanced browser application. And that's the challenge that these young graduate students from Istanbul have taken up. I think they're all aged either 18 or 19, am I right?
Yeah.
So it's very impressive they're willing and able to take on a challenge as complex as this. And yeah, now I'll hand you over to them.
Yeah, our challenge is basically a CAMS visualizer, and today I'll be presenting with Yavuz Arda. We also have a team member. She's currently not here, unfortunately. Firstly, we'll tell you a bit about what the CAMS visualizer is, and then explain much better how it differs from the current application, which has static plot images. And we'll then give an example of how it in practice differs. Then we'd like to show you our current application live with some example data, and shortly explain how it in general functions and talk a bit about the challenges we have had. At the end, we can also receive a few questions. So, what is the CAMS visualizer then?
All right, the CAMS visualizer is actually a web application for plotting and comparing recreational data. You can verify your model data and compare it with the actual observation data to see, for example, the bias of the model data and other metrics. The key point of our application, the current application, is to retrieve and plot the data dynamically from the data files in NetCDF or other formats and plot them on demand.
So how does it then differ from what we have more specifically? So currently, all possible combinations you'd like to verify are predefined. These are usually monthly or triple monthly data sets with models which have been matched before to be able to be compared. But with our CAMS visualizer, it's possible to just give the raw model data and the selection of time, months or dates, as well as models and their if they and comparison of them can be done totally dynamically. In the current application, you can select a few individual sites or a few groups like continental groups to get their raw data. We have expanded upon this greatly. You can in CAMS visualizer plot any kind of plot supported whilst selecting single sites, multiple sites, a few sites you like, or groups just like before, as well as individual dates these models were run at. So it has become much more flexible. And currently, in the application before, it was pretty hard to add anything new or like any new method or any new plot type, as this would require you to generate a bunch of images for whatever data you have, or you'll be limited to adding only new plots. Currently, it is practically trivial if they use this format of having an index and values, which is the only way to show our data currently. What I mean by that is, for example, plotting the data against valid time or sites and so on, instead of, for example, showing it against two different dimensions, which would be a bit more complex. But still, this could be modified in the future to add these if required, which would be much more work to do in the application before, I'm sure. So let's show a practical example. On the left, you see an image from the current application. And on the right, you see its equivalent in the current CAMS visualizer, our web app. As you can see, I mean, there are some small differences, but in general, the idea is the same. And basically, it looks quite similar. But what you can do currently is to easily, for example, change its color. Or if you'd like to, as the data and plotting are actually completely separate in our application, you could also plot it in something else than the current library we are using, which is Plotly. So here I have plotted using Matplotlib as a 3D plot, like a geographical plot. I mean, theoretically, it would be possible to plot it however you would like, just like the 3D plot you are able to see.
Also, this is a general diagram of the communications of the apps. The user interacts with web application. At the startup, the starting data and availability requests manage the options you can select as to let you choose only the selectable options, the options that there are data existing for. Also, we basically have a file system where all NetCDF files are. The Python plotting and availability API then parses them and gets the available data. Also, we have a script that writes those in an availability database, but here it's shown as unimplemented because we initially planned to make a separate SQL database, but it is currently in its entirety in Python. That is a thing to improve. Also, when you choose all the things you want in your plot, you make a request to the API and you get the data for the plot you like. This separation of the front end, the web application, and the API is especially good for if another front end will be used in the future, or even a command line interface.
An idea we had, for example, was to have some kind of also a Python application for showing these, like I believe the one before. So currently, it's very much possible to implement that. As you have the data, you just need to be able to show it in some application. So now we'd like to show how it looks.
Let me share the application. So the current application looks like this. You can select the data you want, the months you want, and the parameters. For example, I want a valid time graph for all these mounts with excess the X bias.
I believe you've selected two of the same somehow, those mounts.
Okay. Yeah, I'm seeing. Also, I can get the graph of operational 21 when I press plot. I think I can also get the plot of this, and if I want them combined, I can also get that. Like this, you can turn them on and off in the Plotly. It is also possible to get a map plot of the data like this with color scaling with the bias value and the size scaling with the sample size. You can zoom in and move however you want. And another thing we have is the two-dimensional histogram. You can get the comparisons like this, and it's all dynamic, and it is all being processed on demand with request to the backend API.
In real time, pretty much.
Yeah.
So something like I'd like to add. So as you can see, our UI is somewhat unfinished, and we'd like to elaborate a bit on why that is. Right now, can you see this?
Yeah.
Okay. So, so considering also that we have just graduated from high school, basically, the biggest problem we had was that we were quite inexperienced with any project, really. Also, a project of this scope, I would say. So, I believe we are a very capable team, but as we need to learn pretty much everything on the go, it all took a while to actually do this. And so another thing, this is especially relevant for the backend, is that we need to firstly understand the data, and then understand what we need to do with the data, and only afterwards could we plan how to get the plots we would like. So we also needed to standardize it to be able to make it work fast enough with such a web application, as the user would like to see the plots as fast as possible, of course. And if it takes, I don't know, many seconds for a plot to arrive, that might not be useful at all to a user. These were definitely very big challenges on the backend. And
this ever-changing backend also affected the front-end development for us. We wanted to make a standardized API request for the data, but we didn't quite grasp how the data will actually be standardized and how the finished structure will look until much later into our project. So with every update on the backend, something in the API broke, and also we wanted to make something that can dynamically generate from the NetCDF files, but it was not actually initially the goal of the challenge?
It wasn't a requirement to better say. So basically, maybe Luke can confirm us on this. Basically, what we needed to do was to show the maybe also pre-generative data, but it's totally currently done on the go pretty much from the start to the end, and I believe that was unrequired.
Also, we, like I said, we didn't understand what the finished product should be and will be until much later into our project, and that all made the front end development very challenging because I didn't know what the user should input for the backend to work essentially.
And this has much to do with our inexperience as well, because we also basically didn't know what we didn't know, so we also couldn't ask for it. So thank you for listening. We'll be happy to take your questions.
Thank you very much, Hakan and Yavuz. Yeah, so that is also part of the program. There's a steep learning curve, and I think the most important thing is that whenever you think something is, ask questions and ask questions from a very early stage on. But I look now at the audience. Are there any questions for Hakan and Yavuz? So maybe you can, or maybe, a comment, you're talking about your own experience, thinking back a few years. Yeah, there is a question.
Are we supposed to be able to see it?
Sorry, can you hear me? Yeah, really fantastic project. Yeah, really great. One question I've got is on you talked about the SQL element. You wanted to was that the data you wanted to store in a maybe SQL-like database or something, or?
I can show that. Like, should we explain that right now? Like, you can maybe ask the question and then we can explain. So yeah. So basically, we have this part of the availability API, Python API, which is responsible for telling the front end which data is currently available. And the thing there was that we need to store this information somewhere. Our first initial idea was to store it in a database, because a relational database would be very fitting for such data. But at the end, we kind of couldn't get it working, so we made it in Python in memory, and then we currently store it basically as a pickle file, just a serialized Python object.
I can go maybe a bit more in depth. So we didn't want to run the availability request on demand because it is fired a lot of, in very high quantities. Every time you make a plot, you fire it up to 10 times, and searching the file system 10 times per a plot weren't going to be very effective. So we thought that we could basically store this availability data in a Postgres environment, which will be a lot faster than manually or on-demand running these queries from the file system. So we decided we wanted to make a SQL database for availability data, but we couldn't manage to get it working in SQL, so we just did it in Python.
Yeah, so the thing, this was actually important. This is actually important for larger data sets, I would say, because the file size of, it just fits very well in a database, and currently we basically created in memory, which means that the whole database should fit in memory, which is not a good requirement for large data sets at all.
Okay, thank you. Any other questions from the audience here? No? Then another round of applause and greetings from Reading. Thanks for joining online. And now we move to the next presentation. We are a few minutes in advance. Wow. So we need to check if, because we have the mentor will be online, that is Jessica Koiner. She is in Bonn. Ah, there she is. And now we're going to the last presentation sorry, of the session, Tales of Dry Land. Seems I need to drink something as well. And then it's about understanding how to visualize trends and explore complex climatic patterns of drought via Jupyter Notebooks. It's a team with Xenophon Karayanis, Yorgos Bekas, Lucy Colley, Madiha Abbas, and Marina Korpulinga. And Marina, you want this microphone or you want you prefer that one? Put it based on the... Yeah, we would have put it higher up.
Okay, I think I can start, right? So, hi and hello from Bonn. I'm happy to introduce...
Jessica, sorry. Jessica, wait
Yeah.
1 second. We're wiring...
Does it work?
No, we are wiring Marina. 1 second.
Okay. Otherwise I use...
No, wait.
Yeah. So at the end, this is the best. Okay. Okay, now we're ready.
Okay.
If
So I can start now?
Yeah.
Perfect. Yeah, hello from Bonn. I'm happy to introduce our team consisting of George, Marina, Lucy, and Akis. So the idea behind our project was, if you go to the next slide. Yes, perfect. Was actually very egoistic, to be honest. Here at ECMWF, we have created this new data set, which we call ERA5 Drought. It's essentially a data set of drought indicators, which are calculated using the ECMWF reanalysis that exists since 1940 to today. And this data set is updated also near real time, so we get an update every month of the state of the drought globally. And I have a lot of friends and colleagues, and we also get a lot of media requests actually that ask us about specific drought events, such as, for example, the very recent drought in Brazil. And we got a lot of questions like, this must be the worst drought so far. And it actually takes a lot of work to dive into each individual drought and contextualize it. So we thought, like, this is a really nice exercise for people to get familiar with these data sets, and also to help us to create reproducible Jupyter notebooks that we can actually hand out to others and say, look, you just need to change the region and you can analyze this particular drought yourself. So this is how the idea for this project was born. And with this, I hand over to Lucy for the introduction.
Thank you, Jessica. Could I have the next slide? So as Jessica was saying, our project, we were focusing on the ERA5 dataset. which is a set of drought indicators, as Jessica was saying. We also collated a Jupyter notebook, which we tried to use to tell a story of what we were doing and make it as understandable as possible. And then we also have the notebooks themselves, which we've tried to make as interactive as possible as well. So the specific data we were looking at in particular 2 drought indicators, the standardized precipitation index, which just has one variable, precipitation, and then the SPEI provides a broader understanding because it counts for both precipitation and temperature-driven water loss through evapotranspiration, which is the hard word to say. We also looked at different accumulation windows from 1 to 48 months, and if you saw on the first slide there was a scale of the drought indicators, so -2 being extremely dry, i.e. a severe drought, and +2 being extremely wet. And we looked at the monthly data from 1940 to the current year, provided in net CDF format. So we had 3 main workbooks, recognizing drought events around the world and over time. So mapping current global drought conditions, identifying regions where droughts were currently developing or intensifying, and then generating reports summarizing the severity and geographical distribution of these events. The second notebook, we used the drought events that we identified and specifically looked at the severity of them in terms of the area affected, as well as the persistence, i.e. the duration, and if any of those drought events stood out as anomalous. And then in the third notebook, we took some other data and tried to identify if there were any primary drivers behind those drought conditions. So I'll pass over to Marina to talk about the first notebook.
Okay, that's my part. We dive deeper into the first notebook, that is the Time Machine notebook, and it's titled in this way because it is designed to exploring the drought events across the globe and over time. This first notebook is aimed for Oops, sorry. This first notebook is aimed for people that has little or no experience in analyzing climate data. So what we wanted to achieve is providing them with basic tools to explore this data, and at the same time, yes, at the same time, we even want that everyone can tailor his or her specific analysis suited for the purpose that he or she has. So to achieve these goals, we have tried to keep the amount of code inside the notebook as low as possible, moving all the logic and the supporting function in separate Python files. And we insert a set of widget block to give the people the ability to choose their geographic area of interest, their accumulation window, and time period. Regarding the geographical areas, all the countries are mapped in this list, and we have even given the possibility to choose the sub-district inside this country, so even people with low computational power can perform some kind of analysis. Let's check if I said everything. Yeah. So we can let's go through some of this analysis. The country chosen for this presentation is South Sudan. The accumulation windows is 12 months, and the August is the reference month. The previous chart, please. Yes, this one. An easy way to approach the analysis is by visually exploring through a set of maps the evolving of the drought condition, and this can be done in a time-lapse format. So in this way, we can have a global vision of the entire country. As we can see in this map, the brown areas are those where the drought events are more severe, while the green one is where there is a wet condition. As we can see along the years, the 2023 was a critical year for drought condition. So given this first observation, we can move to the next charts, because once we have this preliminary observation, we can check our data looking for some statistical measures. In particular, now we can see a scatter plot where the user can compare the median and the media and the medium value, and in this way have an idea of the central tendencies. Instead, with the following box plot chart, we can have a more comprehensive view of the data distribution, looking even at the minimum and the maximum values of the range, the quartile, and the possible outliers. Next slide, yes. When we have found a peculiar event in a specific month of a year, we want to give the user the ability to check if all the other months in this year experiment the same conditions. As we can see in this example via a line chart, we can see that in this case, for all the year 2023, the South Sudan experiment drought events. Please, next slide. Now we can have a more comprehensive view combining months and years via two kind of stripe charts. The first one put the months and the years along the x-axis. Instead, the second one, stripe chart, that is yes, show the years in the x-axis and the month in the y-axis. In this way, we can have a global overview of the tendency of the drought in a geographic area, and both these charts can be created selecting the range of years. So now for this example, we have chosen from the beginning till the current year, but for people that has not the computing power to reach all this result can even choose a smaller range of data. Please, the next step. Yes, finally, another important issue in evaluating drug events are the accumulation windows. In these such area charts, let people to check how the accumulation windows may vary according to the period that they are referred. In this case, we have compared 1 month accumulation period, 3 months, and 12 months. And so this chart can help everyone to compare the short-term and the long-term drought events. And this is the last chart of, this was the last chart of the first notebook, but we have even an additional notebook focused just on the current drought events at a global scale. So in this case, we can have a complete idea of the evolving of the drought globally, and at the same time, there are even the possibility to get a list of sorted list of the countries that are experimenting drought events in a certain year. And now I give the floor to George that introduces us to the analysis of drought events. Thank you.
Oops. Thank you, Marina. So the second workbook was focused on, after detecting, identifying drought events in a region, to set some baselines and then identify extreme events. Again, we still have South Sudan as our area of interest, and we can see the drought classification over time on this stripe plot on the left, and on the right we can see a list of drought events that we identified, along with their duration. Next slide, please. So there were two main areas of focus for our analysis. The first one was the duration of the events and the area affected. Here we can see on the left the duration of all the events we identified in South Sudan through the years, and the blue line is the median, which it was 7 months. We have the 10th percentile and the 90th percentile, which can show us which events were extreme based on the history of the area. And it's very clear that in recent years, in the past 20 years, South Sudan had some extreme and long periods of drought. On the right, we can see a stack bar plot that shows the area affected, and the size of the area affected for each type of drought. And again, it's very easily noticed that the last one, which was for more than 10 years, that most of South Sudan was affected. And finally, for each kind of drought, from mildly dry to extremely dry, we can plot maps that shows the area affected and group them into up to 1 month, 3, 6, or more, the 6 months. And now I'll give the floor to Akis for the next.
So for the third workflow, we were trying to identify the drought drivers, which after working on it a bit, we figured that at least the way we tried to figure it out was more of a chicken or the egg case. So to see if there is any correlation between the two, any relationship between the two, we tried accessing ERA5 variables and running Pearson correlation to SPI values. So for the ERA5 variables, what we did was set the same baseline time periods as was with the SPI, which was 1991 to 2020, and based on that, get the anomalies for the ERA5 variables. Those variables we analyzed were the potential evaporation, soil moisture, runoff, total precipitation, and temperature at several layers, And we considered time lags, which means that the idea behind it was to see if we eventually could train a model having the sum of the ERFI values as input to predict SPI values as output, right? Well, we haven't done it yet, to be honest, because we ran some, we identified Argentina as an area of interest, isolated the SPI values for the last decade, and ran Pearson correlation on that. And we did find some linear relationships among several variables. Well, evaporation and precipitation made sense because those are used to compute SPI, but also we found some relationship with other variables. What was surprising though was that we didn't, there was a lower consistency with temperature anomalies. However, based on this, we could go ahead and train a model using those variables at the lag times that we identified that there are relationships, and train a model to predict SPI. Lucy?
Thank you, Akis. So this is our final slide. I'll just summarize what we've done. So obviously we performed data collation and visualization, so cleaning the data and provide a way for users to view the drought events by country, year, time, accumulation window, and also the geographical distribution, seasonal variations, and trends. And then we provided a more advanced analysis, so discovering the statistical measures, mean and median, and ways to compare time periods against the entire data set, helping to identify anomalies and spot trends and understand drought evolution. And then also mapping out current global drought conditions, classifying droughts, and hopefully generating reports to kind of track and analyze ongoing droughts. What we've learned, a huge amount. So how to understand the SPI and SPEI indices, which is a new concept to most of us, to analyze the drought events, and also how to use these to classify droughts in terms of the severity and duration. And then, as Akis was talking about in the last couple of slides, looking at other external factors which may contribute to these drought events. Potential next steps would be a further exploration into these drought drivers, and also looking at additional data such as fire, flood, heat wave data, studying global and regional climate models, broadening the correlation investigation, and trying to find non-linear relationships, and as Akis mentioned, training a model to predict the SPI values at different lag times as input. One other idea we had, which the previous team reminded me about, was we tried to make the notebook as interactive as possible, but we did also talk at the very start of the project about a front-end way to do a similar thing, which is a bit more user-friendly. And that's it for our presentation.
Okay, thank you very much, team. You heard the run.
These are the link for the Jupyter book, where you can find the notebook and even the chapters, the introductory chapters to drought events, and just a few things.
Sure.
I'm not sure if we have already said it because I'm a bit emotional, but these data are not yet available to the public. They will be with the launch of the new CDS platform in autumn, that will be in autumn. So stay tuned, because we update the notebook to get the data from the CDS instead from the actual server. Thank you.
Excellent. Thank you, George, Lucy, Akis, and Marina. So, questions from the audience? First there, yeah.
Thanks for the very nice presentation, and yeah, really nice work on the drought analysis. Yeah, so it's noticeable, it's really striking how much drier the region got over the period. So I was wondering if you had a chance to look at soil moisture at all. I know it's in your perspectives in the future, but looking at particularly the deeper layers to see if there's any trend in soil moisture which might have contributed to this drought.
So that was the idea behind running Pearson correlation on the data. One of the issues was that it was too slow to run, so that's why there isn't a notebook for that. It was done through script, and because initially the notebook, the connection, the tunneling was timed out so many times, we logged the result and got to that later. We did find some correlation, as you saw in the slides. However, because that was run only for one country for 1 decade, I'm not sure how reliable that data is. So as a future step, there has to be some correlation with soil moisture at different levels. But as a future step, it would be to broaden the areas and the time covered when running those correlation tests.
Okay, thanks a lot.
There's another question here.
Yeah, thank you for the presentation. I was wondering if you also include some explanations into the notebooks. For example, it might not be trivial for an unexperienced user to choose what accumulation period makes sense, as an example.
The first notebook is explained in detail. Every step is explained, and there are suggestions about the kind of analysis that the user can do with the charts. Going along with the other notebooks that are more complicated and are more for experts, the amount of explanation is less, but if it thinks that could be useful, we can implement it.
Well, if we have a minute or two, I could see Emma's going to go to the Jupyter book.
No, I can.
Akis, can you repeat? I'm not sure if I understood.
Yeah, if we have a minute or two, we could go to the Jupyter book to see what's as an introduction.
I don't know if we can.
I don't know who.
Maybe you, Akis, if you share your screen, maybe we can.
Oh yeah,
show,
that's what I mean.
Because
now. So this is the Jupyter book.
Keep it short, though. Okay.
yeah. No, what I was relevant to the question, the last question. There is some introduction to what is climate, data sources, the files we get, and some description of what data that are presented in this book are, right? So an explanation about the indices we use and the values we use. And then you get to the different notebooks that we presented earlier, right? But yeah, I posted the link on the YouTube site as well. So if you want to have a look, to go to the Jupyter book.
Okay, great. Thank you, Akis. Then, if there are no more questions, another round of applause to the team. Thank you very much. We come now to the last sessions. We have some live demos, so it will be a little bit more, again, showing things. And we have 2 more presentations. I would like to keep your energy level up. I'm not that good in entertaining. So there are some yoga breathing techniques. We don't do that. I spare you that. So, and I would like to introduce the Scott Logic team, if I may say it that way. So we have a lot of speakers. There's Tim, Sebastian, Mike, Max, Ben, and Richard. Luke is not here, I think. Sorry. And the project is the Verify project. and the goal is to help improve the air pollution forecast model to be more responsive. And Miha is one of the mentors and said that he would introduce the team and the project.
Gladly. Thank you. Yep, so another CAMS-related project. So we talked already a little bit about the verification. We produce a lot of data sets and a lot of very kind of prominent data sets as well. And one of the probably most visible or most kind of used are the air quality forecasts for CNN. So we provide air quality forecasts that are used in CNN air quality bulletins. And we do a lot of internal validation. We use official data sets from Europe, from North America, from Japan. But the problem is that we are trying to do global forecast. And a lot of areas in the world don't have a good official observation networks, or at least not easily accessible. So there are kind of these citizen science or unofficial air quality observation networks, and we really wanted to see what is the potential of this data set. Is there something that we should be using, and how should we use this data in our kind of day-to-day work? So by some crazy stroke of luck, this team answered our challenge, and I'll give the floor to them to present what they've done.
Okay, yeah, thanks, Miha. So we're lucky to have quite a big team. We're mostly from a consultancy called Scott Logic, but we're also joined by Seb here from the University of Bristol, who's a climate scientist. So that was we're quite a good combined team. And we're supported by Mark, Miha, and Johannes. So first of all, we'd like to talk a bit more about our goal. So our goal was simply to develop an online dashboard for displaying and monitoring air quality forecasts for cities around the world. That's sort of the headline. And an example forecast is shown on the left here. Sorry, technical issues. Right, hang on.
We are sharing via Zoom. No. Do you have the clicker to change the slides?
It's fine, yeah. So I've got I'm just not sharing the screens, the slides correctly. So
no, we are sharing via Zoom the presentation for the demo.
Yeah, I will get there. Okay. Entire screen.
Didn't switch to Zoom. Their slide they're showing.
Okay. Oh, okay. So, right. Okay. Right. Okay. Yep. Thanks, Seb. So yes, the picture on the left is an example air quality forecast. This is something that CNN show on their TV broadcasts around the world. And it's just a forecast, so sometimes it's not right. And there's an example on the right here of New York. So on the 7th of June last year, the forecast for the air quality was good, but in fact, the air quality was really bad. At the time, there were various sensor networks doing lots of long-term evaluation, lots of data being gathered, but there wasn't a quick and easy way to see what the current conditions were like. And unfortunately, the first time that the forecasters knew of the issue was via the press. So there's a need for an online dashboard that gives you a nice, quick and easy idea of what's happening at the moment. In order to provide data for this dashboard, we need to get that information from sensors. There's two different types. There are official, highly highly calibrated sensors and low-cost sensors. The official sensors look a bit like this, and they're clustered in around 3 main networks, and these are centered on Europe, US, and China. And you can see for where they're centered, the coverage is really good. For the rest of the world, it's not so good. There's only a few sensors in Africa and none in South America. The data from these networks is then put into these long-term evaluations of forecasts. Then we've got low-cost sensors that look like this, and these feed into open networks like OpenAQ, together with the official sensors. So this is all the data all in one place. And now we can see that we've got better coverage. Still not amazing, but it's better. We've got a load of sensors in here for South America. But we don't really know how good this data is from these low-cost sensors. Is it reliable and accurate enough to use for improving forecasts? So for that, I'd like to hand over to Seb to talk about the data.
Thank you, Tim. We wanted to start with a brief introduction or overview what kind of data we actually are dealing with, because we spent a lot of time initially during the project working to better understand and to screen the incoming data from the OpenAQ platform. To illustrate this, I just show you this map here, showing like a typical request that we do for our 153 target cities around the world.
Clicker doesn't work.
No, I'm just, it's okay.
He's just pointing.
Okay, sorry. So with a 25-kilometer search radius around the city center for a list of 5 pollutants, so particulate matter, 2.5, 10, ozone, and NO2 and SO2, and for time range in this example for just 1 week. And this map shows you the result that we get. Basically, there are 600,000 individual measurements returned. We already cover with this one data source, so OpenAQ platform, roughly 100 of the 153 cities here, shown as these black dots distributed across 1,300 stations globally. But if you just take a closer look at the data that we get back, was quite some work to do with that. So just showing 2 examples, time series of Vienna, 7 days data for ozone, and for Jakarta, PM2.5. Different colors here, meaning different measuring stations that vary well over that time. And you can already see these time series look quite different. So we sometimes have gaps in the data. We sometimes have very large negative values. So it turned out that some missing values are encoded differently in different data sets in different countries. So cleaning this and converting units and all these things was a large part of our initial work. But this is only the first step of our software platform, and how we, after ingesting this data into a software, to give you an overview about the rest of the architecture, I hand over back to Tim.
Okay, so the architecture of Verify looks like this. At the bottom, we've got 2 components to extract that data from these 2 sources. Those then transform the data so that it can be compared and load it into a database. At the top, we've got the user interface itself, which accesses that data via a published API. And on the left, we've got a store of bitmap images that we can use for creating maps later on. One thing I want to talk about before Max shows you the actual product, and that's something important, the color scheme. So there are a number of different color schemes for AQI levels. We've chosen the European Environment Agency scheme, and this grid basically gives you different levels for the different pollutants, from good in blue through to extremely poor in purple. At the top, there's the top level expression of the air quality, the AQI itself, a simple number from 1 to 6. So now to Max to show the product.
Thank you, Tim. So we've been brave enough to actually give you guys a live deployed demo. Alt-tab. So here is the kind of the landing page that you'll get onto when you visit the link. So at the very top here, we've got the forecast base date. So I appreciate you can't see it too clearly with the... So yeah, the forecast base date, that window, it will basically allow you to, I guess, select where you want to have your forecast starting from. So for each forecast base state, we get CAM's forecast data for 5 days maximum. So from here, I'll also be able to filter those forecast days if I only want to see just a few of those days. And then you'll also be able to kind of see the actual filter that's been applied here with the time range. So for particularly here, we've got the 1st of September, midnight. And so we have 5 days from there, but we've only kind of chosen forecast day 1. So we'll only see the data from that 24-hour time window. So if you then look at the actual grid here, we've got our cities towards the left here, and then we've got all our pollutants and our AQI level on the right. So what's happening here is we've got the cities, they are basically sorted based on which city had the highest discrepancy between the forecast and the measured. And as you can see here, in each individual pollutant, we've got the forecast and the measured as a subcolumn. So for example here, if you look at PM10, we had a forecast of 200.7, which is AQI 6, and then 18.3, which is AQI 1, on this particular valid time here. So since this was the biggest discrepancy within this time range for Dubai specifically, then we display that as the overall AQI level here. And yeah, you can also see the diff here. It's basically saying that we over forecasted by 5, pretty much. And we've obviously got the colors here, but if you're just interested in what kind of pollutant is causing the highest discrepancies, you can just toggle those off just to see the ones, I guess, you're most interested in. Now, if we go into an individual city, if we go into Hong Kong, you can now have a more kind of visual sense of what's going on with the in-situ sensors that are dotted around the actual location. So we've got kind of the same thing, but just as visual graphs. So you've got our overall AQI graph here, of which the black dotted line is our forecast, which is given every 3 hours, and the blue line is our in-situ line, which is given every hour. So this in-situ line is basically showing you the real-time value as opposed to what was forecasted. And this is actually is dynamic. So each of the kind of colored lines on our individual pollutant graphs, they represent a site. So if I kind of deselect this site here, you'll see the blue in-situ line change and shift. This is useful if you've got anomalies and you want to get rid of them. So yeah, that data changes. And you can also obviously add them back in via the drop down here. And we also have a nice map here where you can actually see where each of these kind of sensors are around the map. And you can also do the same thing in here by being able to add and remove sites back in here. And also the charts can be exported as PNGs for, I guess, any blogging or any kind of thing you want to show online. And that's it for the demo. I will now pass over to Mike to show the testing section. Uh-oh. Mike.
Thanks. Hi. So we knew that Verify was going to be developed using an agile approach. So by that, we split the work into small pieces of functionality based around the requirements that we got from the mentors. We then tracked this work using a Kanban board. You can see an example of one behind me here. It's quite a simplistic one, but it's a way of making sure that we try and get as soon as possible something small working that's tested, and then to get feedback from the mentors and to iterate upon that and build. An output of our testing strategy was that any work on a feature that needed to always work or things that should never happen would be encapsulated in test cases. We aim to automate these where possible, and we put them into what's called a regression suite. Regression suites are something that you would run against any new feature that comes in to make sure that you haven't broken something pre-existing by the new work. All other testing was done via exploratory testing. So I've got a picture of a book here which kind of guided some of this, Explore It by Elizabeth Hendrickson. We use test charters as a way to do session-based testing, and it's a great way to find deeper bugs in your software. Okay, so regression testing in the back end was written in Python. We used PyTest as the test framework. This is an example here of a well, it's a PyTest test. It's hitting the forecast endpoint of our API. So this API retrieves forecast data, funnily. And the point of this test is it's asserting that when it's provided with the correct parameters, you get a 200 response indicating that it's been successful back from the system. And what we're doing here, we're using PyTest's parameterization feature to send 2 different payloads in, which represent the API parameters. The top one is different because it's got an extra parameter location name, which is optional. We have tests in the back end which test the API and also all the different parts of the ETL process as integration tests using mocking, and also we seeded data in a QA database. In the front end, the automation was written in TypeScript, and we used the Playwright framework for the automation. It's really powerful. If you haven't used it, I recommend it. We structured the tests using a page object model, which is a brilliant way to separate test code from implementation details. It makes more maintainable tests, and it makes them easier to read when you're looking at them. The actual test that we were doing in the front end, we were mocking, so we would be sending mock data to the summary table on the front page and asserting on the structure of the table that's represented or the color scheme. On the city page, this is an example of snapshot testing that you can do in Playwright. So we'd have tests that would assert that the graph would be represented in a specific way, and if it was no longer presented in that way, when the test takes a screenshot, you get this nice diff representation of what's changed. And I just wanted to finish by talking about regression testing in action, so where we caught a problem using this methodology. We introduced a story, this top one here. As a user, I want to be able to choose the forecast window, and immediately when we ran the tests against it, one of the tests broke. And the test that broke asserted that when you set the date to more than 5 days in the past, you'd get 41 API calls made to a particular endpoint. We got 72, and digging into it, we established that it was not just requesting data for 5 days, it was requesting data up to present. And then when you went into the UI, because as testers we do this kind of thing, and set the date to the year 1900, it tried to make 400,000 requests for over 100 years worth of data and took our application down. But our automation basically caught the problem immediately, and we could fix it. I'll hand over to Seb now.
Thanks, Mike. Can we go back to the presentation? So the Verified dashboard is live now, but it has been an open source project right from the start. So we don't see the current version that is online now as sort of like the end of the road, but hopefully rather as a start of a new platform to really merge the CAM's air quality data and the real-time measurements, and to enable new applications for the future. And I just wanted to briefly mention 2 possibilities that we are already working on. First of all, we decided to make the backend and the API to access our backend publicly available. So this is currently used to run the dashboard, but everybody can access the backend to use the data that we gather and we cleaned basically for their own analysis. And for this, we provide a Jupyter notebook within the repo, for example, to explain how to use this API to get also not only like 1 or 5 days of data, but maybe like a month or 3 months of data for an individual city. So it's very easy to use and explained in this Jupyter notebook. And the output looks like something like this. And people can just use this data then for in-depth analysis or statistical analysis, however they like. And also there's a new experimental feature also on the dashboard now, where we actually go 1 step back and show a global map of the forecast data to make this data even more accessible to a wider audience. And I just want to briefly show you this as well. So this is the dashboard that Max already showed. There's a button at the bottom to actually show the same data in a map view, which is shown here at the bottom. I don't know how much frames come through Zoom here, but should be fine. So basically, this is as we imagine it, as one step back of the table view at the top, which is great for the expert user, for our mentors, first place. But we think more people can benefit from our work, hopefully, in the future. And therefore, we started with this map view now to, first of all, to show the global forecast data as a background overlay, all of the locations that we actually acquired as real-time data for, compared with the data with our forecast data, and then the user can start, like it was in the challenge description, to play and explore basically the underlying data. So this will update based on the selected forecast base date and forecast length. Let's say like goes to something more recent example maybe. And then the user get this timeline at the bottom to really, to just explore, to see how this changed over this forecast length, how the in situ data updates, where are the hotspots, where are differences, what does the model do. You can then always go into more detail by just zooming into a certain location. For example, seeing the forest fires there over South America for the recent days, how this relates to worse air quality in the affected regions, and then you can really start to see what kind of locations we actually have available that might pick up the signal, how does it compare to the forecast data, and we also added functionality to just look at the same data in this globe view to just be able to just explore the data, look into specific regions, to, for example, then also look at the actual grid point information that is in the data. So you can always look at what is actually stored in the actual model resolution there. Look at different variables, for example, to just see how the different pollutants make up the overall air quality index, how this changes over time. And I think there's just a lot to actually just explore for exploration for the user as a first start, and hopefully this might even be transferable to other CDS, ADS data sources in the future. So,
what's the size of the circle?
Pardon?
The sizes of the.
Oh, sorry. Just whoop, the sizes of the circle. Just go back to the world map view. They are, at the moment, they are just scaled by the overall AQI difference, or even in this case, the pollutant difference between the in situ mean and the forecast at that location. So basically, they represent the first row, the diff row in this table. So the data always represents the same data as in the table, but we see it as sort of like a temporal and spatial expansion of the table in a way to explore this. And it's, at the moment, it's just scaled to just guide the eye sort of like to the hotspots. Like if you look at this, like you will always see, okay, there's something wrong with Lima, or some locations really where we overestimate the in situ data quite a lot. So as a first guide for your eyes, basically. That's the idea, but you can configure that. Okay. So this was just like two of the, what we think, quite exciting possibilities, what we can already do with the current platform and might be able to do in the future as well. And I will hand back now to Tim for some concluding remarks.
Okay. Thank you. So yes, in conclusion, I think we can say that we've met our goal. We've got this dashboard available now for forecasters to use, and it's being used pretty much every day to help spot those differences. This is using a lot of data from these low-cost sensors via OpenAQ. And we've got some examples here. The first one for Los Angeles is an example of spotting things as they happen. So we were looking at the tool on the 5th of July, and we saw these big peaks across many US cities. And what's going on here? And it was the Independence Day fireworks. Really clear signal in the data. And the one on the right, that's something from Mark Parrington, and one of our mentors, where he was looking at long-range smoke transport across the Atlantic from the wildfires in Canada. And he saw that a peak of data in the official networks was also being reflected in our tool. So that kind of shows that this open data from these low-cost sensors is going to be useful for longer-term analysis. So I just wanted to finish with a picture of us in action. So yes, it's a slightly staged photo, so some of us striking poses. But it's a real meeting, honestly, talking about process. There's a link there to the product if you want to have a look yourself, and there's documentation in GitHub to describe how we've done this. And yeah, lastly, thank you to the ECMWF staff, Code for Earth team, and especially our mentors. This is not something that ScotLogic normally does, so we've really enjoyed the opportunity to contribute in a small way maybe for reducing the impact of air quality worldwide. So thank you very much.
Yeah, thank you very much, Tim, Seb, Max, Luke. Nice presentation. Are there any questions? Is all crystal clear?
Thank you.
Let me check if there are any questions. There is a question.
It's not really a question, just I think that you should connect to a laboratory in Aristotle University of Thessaloniki that are doing the same thing with DIY sensors, and you could benefit from a meeting. Perhaps you can do stuff together. Just
okay, yeah, if you could put us in touch.
Yeah, so we still have the evening reception. So and essentially the day today is to connect each other. We don't have any questions online. So thanks again for your contribution, for the presentation. That looks very dynamic. Good. Another round of applause to the team. Thank you very much. Thank you. And I would like to ask the next team, I think you have to plug in your computer as well, or how? Yeah. So, yeah, we are coming to an end with the last presentation, last but not least, as we say. So we have the SunVisor project. The idea is to enable the solar energy community to visualize data before downloading. You have to put it on. Yeah, you have to switch it on. No. And we have Sergio in the team, Irma, John, Javier, and I hope I've not. And we have Nube online. Nube, greetings to Bonn.
Thank you.
So Nube was one of the mentors, and Nube will give a short introduction to the team. But let's first check that everything works.
Let me know when the presentation is on the screen, because I cannot see it.
So we are preparing here.
Perfect. Thank you.
So we're getting to it.
Yeah, we are waiting to get in Zoom call.
You need a Zoom call?
Yeah, we need. Okay. Then.
Good. Okay, Lube, we are bringing the presentation on, and then I leave the stage and leave it for the team and you.
Okay, perfect. Yeah, can I start, right?
Yeah, sure.
Okay, so hello everybody from Bonn. I'm really happy to be here today, even we are the last one, so we hope that you can enjoy with our challenge. For me, it has been a pleasure to mentor the challenge together with my colleague Eddie, Julie, James, and Melanie. And yes, thank you very much to the team members, and congratulations to arrive to this stage. We are quite happy with the solution that you have provided for this challenge. And the team members are Irma, Sergio, John, Jonas, and Xavi. So please, next slide. So the motivation for this challenge just was born in the framework of the Copernicus Energy Hub. That is a new initiative of the European Commission implemented by ECNWF, which main objective is to illustrate and facilitate the uptake of the Copernicus data, but also the information that is relevant for the energy sector. So till now, in the Energy Hub, it's possible to access to the different data sets coming from different Copernicus services, but it's not possible to visualize or making comparison from the different data sets. So then we just put an idea over the table and we just put the challenge up to create a prototype web application that allows to visualize and making comparison of data set coming from CITRIET and from CAMS, two of the ECNWF Copernicus services, and put it together in an application that can allow to the solar energy sector to visualize them, but also to have a feeling just before downloading this data. And yeah, this is the challenge, and I think the teams have done very well. So I hand over to Sergio to continue with the presentation. Thank you very much.
Thank you, Nube, for introducing the team, the mentors, and the motivation behind this challenge, the SunVisor project. Here we have the agenda for today's presentation. First of all, I will introduce the project description, the objectives, and the variable selected. Then John will conduct a live demo to show SunVisor capabilities and to show the functions that we have there. Afterward, Irma will deep dive into the methodology, and then Jonander will explain the architecture and the feature work. So next slide, please. Okay. The objective of this project is, as Nube has said, create an interactive and user-centric web application for end users to effectively visualize the data related to energy sector, basically solar sector, from different AC MWF catalogs, C3, ANES, and CAMS, and visualize the data at different time scales, such as historical data, next day's data, and climatic projections. The objectives here for us is provide the renewable energy sector with a new layer of value regarding weather data access and visualization. As we work in the sector, we consider that is a need for our sector, as well as collaborating with ACMWF in this project and get along with all the data in the different catalogs. And of course, enhance our team's data visualization skills. So if we go to the next slide, before moving to the main findings, I would like to explain a little bit the variables that we have selected to visualize in the SunVisor. The ones highlighted in blue are the ones that we are going to see later, and the ones in gray were in the roadmap, but for different reasons they are still not there. So from ERA 5 we have 2 meter temperature, surface solar radiation downwards, and snow depth. From climate and energy indicators, we have surface downwelling shortwave radiation, solar photovoltaic power generation, and also 2 meter temperature. And from CAMS, we have global horizontal all sky irradiation and clear sky irradiation. For this proof of concept, we have downloaded 5 years for each variable, and we expanded the bounds that we have initially, and it covers especially almost all Western Europe. So having said that, I will hand over to John that will demo the SunVisor application. So John, the floor is yours.
Hello everyone.
So I'm going to show you the application that we developed. So the first step that I want to show you, we had an API. In this API, we had two principal endpoints. The first endpoint is to retrieve the whole structure of the variable that Sergio mentioned. So in this structure, we get the name, unit, icon, aggregation, the models that we are going to use in the user interface. And the second endpoint, that this is the important endpoint. Here we have the all information that we pre-process and with the aggregation that we selected for. In this case, this is an example for the temperature, as you can see here, and this comes from the RFI, and we are using aggregation only, and this is the value. So this is very interesting for the user because we are offering the possibility to download the flat data directly if they don't want to use any user interface. So now let's move on to the user interface. So, okay. As you can see here, this is the area that we selected to show all the data. We include some nice functionality for the first user. For example, we include a short tour guide for the user that inside the first time in the web application. So as you can see here, we indicate the user, select the variable, choose a point in the map, and finally we can see the results in this slide that we are going to show you in a few moments. So for this example, I'm going to show you to select temperature, and for example, I'm going to press here in Paris. And as you can see here in this window, we have the location that we selected, the models where we are getting the information, and the aggregation that we selected by default. Here, the user had the possibility to change the option, and we are offering a short description of the aggregation that we are offering. So in this case, we had monthly, but if we want yearly, we had this possibility also by month. Another important thing here is that we are offering also the user the possibility to download the data directly in CSV file. So in this case, for the temperature, for example, in Paris.
Yeah.
So,
for example, let's say that you are a user who is interested in solar data to build your solar plant. So in this case, this variable is very important because the temperature affects the efficiency of your panels. So in this case, you can compare between this point and another point. Please, John.
So this is the other important functionality that
this
we
is
add.
Yeah, this is one of the key features of this application. You can compare between different points. So in this example, you could find a better place with better temperatures for install your panels, and you can select 4 points. Yeah.
For example,
at maximum.
Spain, and here to see the difference.
Yeah, we can compare the difference between the 4 points. So, for example, we can now select another variable. For example, if we are interested in one of the radiation variables, which are very important for the solar sector. Let's say, for example, now let's again select new points. Let's say that we want to build a plant in Reading.
So
okay.
Here.
Now we think also that a good place is Bonn and Bologna, for example. Okay.
And why not Spain?
Okay. Okay. So here you can clearly see a difference. So for this user, it's very easy to compare between these 4 points and to have a better decision of the place where he wants to build his solar plant. And also you have the option, if you see behind the plot, or below the plot, you have a slide, and you can zoom in your data to have a better view of the information. Yeah, and for example, we have different temporal aggregations, as you see, daily, monthly, yearly, as John was mentioning. So for some variables, maybe you are interested in the daily time series, or for example, for radiation, I think it's very important by hour. You maybe want to check the best hours or something like that. So yeah, that's very good.
So, and finally, here in the website, you had a short summary of the documentation, and also in GitHub you had available of the information, the technical information. So now we are going to talk about how we did it, all this platform.
Okay, yeah. So yeah, thank you. So, okay, so now that you have seen the visor, let's better understand how it works and what's behind it. Okay, so as many of you know, the European Centre offers a wide range of meteorological and climatic data, but each data set can be accessed from different places and in a different way. So imagine that you are a user coming from the solar sector who doesn't know much about meteorology, but you need to access solar data. Well, I think in this case, the user would be a bit lost. And apart from this, there's also a challenge of downloading massive data sets like ERA5, which covers 80 years of data, because processing such a large amount of data, I think, can be overwhelming for the user. So what's our solution? We want to unify all this data. Okay, so the CDS and ADS service offer the option to download the data in NetCDF and GRIB format. So for our project, we have decided to download the considered data in NetCDF format, and then we apply pre-processing to calculate the different temporal aggregations, such as the daily average temperature or the cumulative rainfall per year. You can see here a list of the complete aggregations we have chosen. And now, and here comes, I think, one of the most groundbreaking parts of this work. We transform this data into a format called SAR. And this allows us to combine and organize data from multiple sources, reduce file sizes, and optimize access times, which is also very, very important. So to have an idea of what I'm saying, here's an example of a NetCDF file compared with its SAR counterpart. So you can see in these plots that the SAR file is 40% smaller and offers also faster reading times. And I have to mention here that for this test, we have used only 5 years of data, but we have seen that the optimization increases as the volume of data grows, so it's very nice. So now, for this proof of concept here, we focus on a small region in Europe, downloading 5 years of data for the variables of the selected models. Here you have an example of a time series of the surface temperature for one point in that region with an hourly resolution. And then we, as I mentioned, we process and transform this data into SAR format. We mainly use Python with XRI, and then we store this data in a virtual machine so that the API can access to this data and display it in the web application. Okay, so now I think it's time for my colleague John to show you the architecture.
Thank you, Irma. Okay, now it's time to speak about the architecture. So we have developed 2 projects. The front-end one is a website that is developed with React and TypeScript, and it has HTML code. We have to mention that we are using Vite, and with Vite we can package all the libraries and launch it locally in less than a second. So it's easy to work with that technology. And for the charts, we are using the HCharts library. the other project that we have developed is the SunVisor API. It's a Python code. We are using the FastAPI, the library, and there are developed 4 main endpoints. Here you can see the first one, there is /API and /variable, and the variable info. The first 2 are related only to show the variable information that we have preprocessed and we are offering through the website. And the other 2 endpoints, the API point and Solar data, are related through the data series. So also, in the server, we have a property file. As you can see here, each file is one variable with different properties. Here, for example, we can configure the conversion formula, for example, for the temperature. We are receiving in Kelvin, so we are converting it to Celsius degrees. Here, the technology for the reading files is XRI with SAR library. This is an example of the 2 variables, 2 endpoints that we showed before. Are in a JSON format, and the idea is to use the web for the normal users, that they can navigate through the web and download the CSV files, and the other part for the developers, they could use directly the endpoint and use it for their developments. And here it's important to mention that in this property file, each variable that we configure here will be we have a repercussion in the website. All the website is dynamically loaded through the API, so all the information that is stored in the server will show here dynamically. So we can put a new variable or we can remove it without doing a new development. So continue with the current deployment structure in the server. We have a server in a European Center site, I think, and here to deploy the 2 web servers, and we only have the 80 port available. We have installed an Nginx working as a reverse proxy server. So here is a little configuration that you see in black. Now, when the user is giving new requests to this Nginx server, by default, all the requests will go to the web, except the ones that starts with /API. So inside, there are 2 applications running in localhost, and the engine is the gateway that will redirect all this information. And now we go to the future conclusions and future words. Sorry. So we have put 4 main points. The first one, we thought maybe is the most important one, is focus in the data. Now all the preprocessed data or on the downloaded data is stored now in this virtual machine. So for the future, we think that it's important to separate in different layers the data in one server or in different type of server. We think maybe data lake or something that this technology will be very interesting. Also, could be stored in a standalone servers or in an on-premise structure. But we think that the data should be separated with the applications. Also, in the data, we have to mention that we are using now SAR files, and this technology we are using by default configuration with a little changes, but we know that if we delve deeper in the configuration of this technology, we will improve a lot the velocity to access the data and also the compression of this data. The second point, the web and API scalability. We know that if we will offer this data to hundreds of thousands of users, with one API, it will be impossible. So we will start to thinking to put this technology in an elastic cloud solution. There are many providers that offer on-demand services that if you have an increased demand, you can put new virtual machines, or if demand is 0, only to have one. So it will repercute in the cost of the solution. The third point regarding the DevOps and CI/CD pipelines, in this POC, we have developed and deployed all manually. So the next step will be to connect the code with end resources. And also to take into account to have more than one environment. The prod for the clients and the development and quality for the internal developers. And the fourth step, the user management limits and cybersecurity. We also know that this API couldn't be open to all the users, so it would be nice to have an infrastructure that could have all the users authenticated and authorized. So also control all the requests that we receive and put some limits in this kind of requests, or by user or entire by all the server. And final aspect, cybersecurity, we don't have to forget this step. We know that to continue the good practices in this area is very important. So we would like to continue working in this area and to put all the needed security in different layers, starting from the starting requests and the security of the authentication of the users, and in the last part will be in the data lake part. And we know that if we implement all these features, so we know that the SunVisor project will be a product. So thank you.
Yeah, thank you very much, team. That was very interesting. I'm a geographer, so I could relate to a lot of aspects here. That was very interesting. Are there any questions from the audience? I know it's late and it's the last presentation. None. Do we have any online? Aging is not the best. So there are no questions online, but we will have the opportunity. We'll meet each other later, so I'm sure there are a couple of questions and I will come up also with some. Thanks again to the team and to the mentors. Round of applause.
Thank you all.
Very well done. So, and we come to the wrap-up session. And yes, Esperanza, please join me here. Yeah, so it's the wrap-up, and we have to say we had an exciting way behind us. It was interesting, and yeah, it's nice. So, and so the 2024 edition was really fantastic. We had 13 projects with more or less 50, and I say more or less because we had changes in the team, more or less 50 participants, 50 participants, 40 mentors, and that is also a great indicator that our mentors are supportive and colleagues are supportive of the program, and also that Code for Earth is important for ECMWF colleagues, and I think we get a lot of support from the colleagues. Special thank to our partner organization, Helmholtz Zentrum Herion, Martin and Johannes. Unfortunately, Martin, we had a hiccup in the morning, but for Martin, we think of you. And IFAB was also very supportive. And a special thank to the Compla team in the background. Hey, managed. And also our colleagues here, Andy Gundry and Mike Morrissey, they were They had positive vibes yesterday evening and this morning, so they were super helpful. And I would also like to thank Olga, Olga Lögle, a new colleague of ours, who chimed in wherever necessary. Good, and now I think we can say goodbye.
Yes, congratulations, everyone.
Yeah,
yes.
for well.
Yeah, and we have prepared. Yeah.
Goodbye to the online audience. Okay, perfect.